The first thing the camera sees is not a monster. It is a footprint. A shallow dent in pale gray mud, pressed there by something soft and slow, already beginning to lose its edges beneath a powder of falling dust. There is no wind here, no rain, no seasons passing over it. Nothing should be able to erase it quickly, and yet the floor is never still. It is being buried, grain by grain, by the remains of a world that lives thousands of meters above. In the headlight of a descending machine, the footprint looks almost human for a moment. A small hollow, a trace, the kind of mark a body leaves behind when it is moved through a place where no one expected motion. Around it, the Pacific seafloor stretches outward into darkness. The beam only reaches a few meters. Beyond that, the largest ocean on Earth becomes an absence so complete that distance loses its meaning. The water is black. The pressure is absolute. The temperature is close to freezing. And in that silence, something moves. A pale animal, almost transparent, lifts itself from the mud. It has no hurry in it. It drifts more than walks, bending with the faint current, feeling the world through limbs that look too fragile for a place carrying the weight of an entire sea. Behind it, a sea cucumber inches forward, like a living piece of shadow. Somewhere farther away, unseen, a fish with no scales passes through the dark as if it were part of the dark. This is the bottom of the Pacific Ocean. Not the blue surface on postcards, not the glittering water beneath ships, not the bright coral gardens where sunlight breaks into gold. This is the Pacific after light has died, after warmth has thinned, after the familiar world has been left behind one layer at a time. It begins above, where waves fold over each other and seabirds cut through the air. The ocean there feels open, restless, alive in a way humans understand. But beneath that moving skin, the water deepens into another planet. The colors go first. Red disappears, then orange, then yellow. Blue lingers the longest, fading slowly until eventually even blue cannot follow. The sea becomes a column of darkness, and then, far below the last shimmer of daylight, the bottom waits. For a long time, people imagined that almost nothing could live there. The deep seafloor seemed too cold, too dark, too crushed by pressure, too far removed from the sun. It was pictured as a desert of mud, a burial ground, a place where the ocean's story ended. But the deeper humans sent cameras, nets, landers, and submersibles, the more the emptiness began to answer back. There were tracks in the sediment, burrows, shells, soft bodies moving in the silt, fields of animals gathered around cracks in the earth, forests of tube worms rising in darkness, shrimp swarming near black chimneys where water hot enough to scald metal poured into a sea colder than winter. Clams and mussels growing where methane seeped silently from the crust. Amphipods arriving at bait like tiny ghosts. Microbes hidden in mud, in rock, in the bodies of animals, turning chemistry into flesh. At the bottom of the Pacific, life does not announce itself with abundance everywhere. It appears in scattered signs: a track, a hole, a mouthpart, a drifting pulse of light, a white body against volcanic stone, a slow animal crossing a plain so wide it could swallow countries. The strangeness is not that the deep ocean is lifeless. The strangeness is that it is not. The descent begins with brightness. At the surface, the Pacific is all movement and reflection. The sun breaks on waves, and every crest seems briefly made of glass. Plankton drift in the upper water, small as dust, yet powerful enough to feed the world. Fish flash silver beneath them. Squid rise and fall. Turtles cross open water with the old patience of animals that knew the sea long before humans named it. Here, life is tied to light. Phytoplankton use the sun to build themselves from carbon, and in doing so, they become the first meal in a chain that reaches from tiny drifting grazers to tuna, sharks, whales, and birds. The surface looks empty from far away, but it is busy with invisible work. Every day, sunlight is being converted into bodies. Then the light begins to weaken. At first, nothing feels dramatic. The surface is still above. A human diver could still look upward and see the wavering brightness of air. But as depth gathers, the sea starts removing familiar things. Warmth thins, sound changes. The body, if it could remain, would feel the pressure rising with every meter, a steady tightening from all directions. The water does not press like a hand, it presses like a law. By 200 meters, the sun has become a memory of the sun. This is the edge of the twilight zone, where animals hide in dimness during the day and rise at night to feed. It is one of the great migrations on Earth, happening every evening in the open ocean, as billions of creatures ascend toward the surface and then sink again before dawn. Lanternfish, krill, squid, gelatinous animals shaped like ribbons and bells, all moving through the dark in a rhythm older than agriculture, older than cities, older than the names of stars. Many of them make their own light. A flash appears, then vanishes. Another blooms green, then blue. Some lights are warnings, some are lures. Some break the outline of a body so predators looking upward cannot see a silhouette against the faint glow above. Bioluminescence is not decoration down here. It is language, camouflage, hunger, fear, invitation. The deeper the water gets, the more the ocean seems to become a night filled with private signals. The Pacific is so deep in places that the descent can feel less like traveling downward than moving through time. A piece of organic matter falling from the surface may take weeks or months to reach the bottom. A dead jellyfish, a fish scale, a pellet of waste, the dust of plankton shells. Together, these fragments form what scientists call marine snow, and in the darkness, it falls almost continuously. It is a snowfall made of former lives. From above, it looks delicate. Beneath a light, each particle drifts slowly, turning in the water as if suspended in thought. But to the animals below, this falling matter is the connection to everything lit by the sun. It is food, however sparse. It is proof that the surface exists. Down through 1,000 meters, 2,000, 3,000, the water becomes colder and more stable. The daily changes of the surface no longer reach here. Storms may build enormous waves overhead. Ships may cross. Satellites may watch cloud bands turning. But the abyss barely reacts. Its world changes slowly. Its clocks are not human clocks. At 4,000 meters, much of the Pacific floor lies near the depth of the abyssal plain. The word plain sounds simple, but the scale is difficult to hold in the mind. These are not small, empty flats between dramatic features. Abyssal plains cover enormous portions of the ocean floor, making them among the largest habitats on Earth. Many lie beneath water so deep that mountains could stand on them and never break the surface. The bottom appears soft, pale, endless. Fine sediment has been settling here for millions of years, smoothing the rough volcanic crust beneath it. In some places, the mud is made partly of microscopic shells, falling from the upper ocean and accumulating so slowly that a human life would barely mark its thickness. In other places, below depths where calcium carbonate dissolves, the seafloor becomes redder, darker, more clay-like. a patient archive of dust from continents, ash from volcanoes, and the remains of creatures too small to see. The first impression is emptiness. A camera on a remotely operated vehicle points forward, and the beam reveals the same scene again and again. Mud, ripples, a stone, a faint track, the round shadow of a burrow, a brittle star spread like a tiny compass, a sea cucumber feeding with soft tentacles, a small fish resting close to the sediment, its body shaped by a life with no need for speed. Then the vehicle moves a little farther, and the emptiness begins to change. A sponge rises from the plane, anchored to a small patch of hard ground. Its body is pale, glassy, intricate. It filters water that seems to have nothing in it, but the water is never truly empty. Bacteria drift through it. Dissolved molecules pass through it. Specks of organic matter move in currents too faint for the human eye to measure. The sponge lives by patience. Nearby, a holothurian, a deep-sea sea cucumber, pushes across the mud. It looks almost like an abandoned glove, come alive, gathering sediment into itself and digesting whatever nourishment it can find. Its work is unglamorous, but essential. On the abyssal floor, feeding is often a matter of sorting through the ruins of the upper ocean. The animals here are not failures of evolution. They are not incomplete versions of shallow water life. They are exquisitely fitted to scarcity. Many grow slowly. Many reproduce in ways that depend on the rare meeting of bodies across immense distances. Some wait for years for one large event to change everything. A dead whale sinking from above, a tree trunk carried out to sea and delivered to the bottom, a landslide of organic material, a bloom at the surface that sends a brief richness downward like a distant harvest. In the abyss, survival is not always a chase. Sometimes it is a form of listening. The Pacific floor is not one landscape. It is a continent hidden underwater, except larger than any continent and far less known. There are plains, hills, fracture zones, ridges, seamounts, trenches, canyons, volcanic arcs, old lava fields, fields of metal-rich nodules, places where the crust is young and hot, places where it is ancient and cold. The bottom is often imagined as a single depth, a single darkness, but it is a world of provinces. A seamount rises from the abyss like an island that never reached air. Its slopes interrupt deep currents, and the water moving around it can concentrate food. Corals may grow there in the cold, not the bright reef corals of shallow tropics, but deep water forms that build slowly in darkness. Sponges cling to rock. Crinoids lift feathered arms. Fish gather in the current, facing into it, taking what the water brings. These mountains are way stations. They offer hard surfaces in a place where mud often dominates. They create turbulence. They connect depths. Animals that may be rare on the surrounding plain can become common along their flanks. The Pacific is filled with such submerged mountains, many still unmapped in detail, many never visited by human eyes or cameras. Between them, the abyssal plain spreads out again. Here, the pressure may be 400 times what humans feel at sea level. A hollow space filled with air would collapse. A human body would not survive the descent without a pressure vessel. But many deep-sea animals do not experience pressure the way we imagine it. They are mostly water, and water is difficult to compress. Their bodies contain few gas-filled cavities. Their proteins, membranes, and molecules have been shaped by generations to function in conditions that would ruin surface life. The deep does not crush them because they belong to it. Still, pressure matters. It influences chemistry. It changes how membranes behave. It affects enzymes and muscles and nerves. Some deep animals use special molecules to stabilize their proteins. Fish living near the known limits of fish depth carry compounds that help their cells resist pressure, though even these adaptations may have boundaries. Below roughly 8,000 meters, fish become rare or absent, and invertebrates take over the deepest parts. On a baited camera lowered into the hadal zone, amphipods may appear in clouds. They arrive from the dark with startling speed, pale bodies bending, antennae searching. Their world is poor in predictable meals, so a sudden fall of flesh becomes a summons. What seems grotesque to us is abundance to them. A dead fish on the seafloor is not a death scene, it is a temporary city. The bottom of the Pacific is built from such temporary cities. A carcass falls. First come the scavengers, tearing at soft tissue. Hagfish may knot themselves against the body to gain leverage. Sharks may visit at lesser depths. Crabs, amphipods, worms, and countless smaller animals reduce the body piece by piece. Then, after the flesh is gone, the bones remain. In whale falls, those bones can feed communities for years. Lipids locked inside the skeleton nourish bacteria. Sulfide is produced. Chemosynthetic microbes grow. Animals associated with chemically rich habitats arrive, some of them related to those living at vents and seeps. A whale that once breathed at the surface becomes a deep-sea ecosystem. It is one of the strange continuities of the Pacific. A song in the blue water may end as a feast in darkness. The animal that rose to breathe air becomes part of a world where air has never been. In the deep sea, nothing is wasted quickly. It is transformed slowly. The abyssal mud itself is alive, not visibly most of the time, but intimately. Microbes live in the sediment in numbers that are difficult to imagine. They break down organic matter, cycle nutrients, influence chemistry, and persist in environments where energy is scarce. Some may divide only rarely. Some exist at the edge of metabolism, a kind of life so slow it almost resembles geology. The boundary between living process and planetary process becomes blurred down here. A current moves, a particle falls, a microbe consumes, a worm stirs sediment, a nodule grows by a thin chemical skin, a trench collects carbon, a vent releases minerals from the crust. The planet is not a stage for life at the bottom of the Pacific. The planet and life are entangled. Manganese nodules lie scattered across parts of the abyssal seafloor, especially in regions like the Clarion-Clipperton zone of the eastern Pacific. They look like dark potatoes resting in the mud, but they are mineral formations that can take millions of years to grow. Layer by layer, metals precipitate from seawater or sediment pore water, forming lumps rich in manganese, nickel, cobalt, copper, and other elements. To industry, they are resources. To deep-sea animals, they are habitat. A small sponge may anchor to one. A worm may live beside one. Microbes may colonize its surface. In a landscape dominated by soft sediment, a hard object can be the difference between drifting and holding fast. Remove the nodules, and the landscape changes not for a season, but for spans of time beyond any human project. The abyss heals slowly, if it heals at all in the way humans mean. There are tracks from old experiments on the seafloor that remain visible decades later. A machine passes once, disturbing the mud, and the mark stays. The sediment does not close quickly. The currents are weak, the animals are slow to return. What looks like emptiness turns out to be vulnerability disguised by scale. The Pacific bottom does not ask to be dramatic. Its fragility is quiet. Far from the abyssal plains, where tectonic plates pull apart or collide, the bottom can become violent in a different way. At mid-ocean ridges and back arc basins, seawater seeps into cracks in the crust. It sinks, heats near magma, reacts with rock, strips minerals from the earth, and rises again through fractures. When it bursts back into the ocean, it may emerge as a shimmering plume, sometimes hot enough that the chemistry of water itself becomes strange under pressure. These are hydrothermal vents. Before they were discovered in the late 20th century, many scientists assumed that all rich ecosystems ultimately depended on sunlight. Even deep animals were thought to depend on food raining down from above. Then, cameras reached the Galapagos Rift in 1977 and found communities gathered around warm springs on the seafloor. Clams, mussels, crabs, strange worms, and dense microbial life. The discovery changed biology. It showed that ecosystems could be powered not by photosynthesis, but by chemosynthesis, microbes using chemical energy from the earth to build organic matter. At a vent field, the darkness is no longer empty. It becomes crowded. Black smokers rise like ruined towers from the seafloor, their chimneys built by minerals precipitating when hot vent fluid meets cold seawater. The fluid pours out, dark with metal sulfides, twisting upward like smoke, though there is no fire. Around the chimneys, life gathers in impossible-looking abundance. Tube worms may stand in clusters, their red plumes extended into the water. Mussels crowd the rocks. Shrimp graze on bacterial films. Crabs move through the heat gradients with careful precision. The animals are not feeding on sunlight. They are feeding on geology, indirectly. Microbes take hydrogen sulfide, methane, hydrogen, and other reduced chemicals and use them to fix carbon. Some live freely as mats. Some live inside animal tissues as symbionts. The famous giant tube worms have no mouth and no digestive tract in the ordinary sense. Their bodies house bacteria that make food for them. Their red plumes collect oxygen, carbon dioxide, and sulfide from the water and deliver them to the microbial partners within. A vent animal is not always one organism in the simple sense. It can be an alliance. The water around a vent is full of contradictions. A few centimeters can separate near-freezing seawater from fluid hot enough to be lethal. Toxic compounds become nourishment. Darkness becomes productive. The deep sea, often defined by scarcity, becomes locally lush. Yet this abundance is unstable. Vents do not last forever. A chimney may collapse, a flow may shift, a field may die. The animals living there must be adapted not only to extremes, but to impermanence. Life at vents carries the atmosphere of a city built beside a volcano. It thrives because the earth is restless. In the Pacific, hydrothermal vents are tied to the movement of plates. The ocean floor is born at spreading centers, altered by seawater, carried outward, bent downward into trenches, and returned toward the mantle. The deep ocean is not just a basin holding water. It is part of a planetary engine. At the East Pacific Rise, where plates spread quickly, vent fields can be dynamic and fast-changing. Lava can erupt. Communities can be destroyed and recolonized. Larvae drift through darkness, searching for chemical cues. A new vent opens, and within a short time, microbes arrive. Then grazers, then larger animals. The sequence is not identical everywhere, but the pattern suggests a deep resilience. Life has learned to find the Earth's openings. A vent field in darkness can look like the origin of something. Not because it is peaceful. It is not. It is hot, toxic, mineral-rich, unstable, and unforgiving. but it offers energy in a place where energy is everything. It hints at how life might persist on worlds without sunlight, beneath ice, near rock and water, where chemistry replaces dawn. This is why deep-sea vents often appear in conversations about Europa, Enceladus, and other ocean worlds. The Pacific bottom becomes, unexpectedly, a rehearsal for imagining life elsewhere. But even this comparison can make the deep ocean seem too distant, too alien, as though it belongs more to space than to Earth. It is alien. And it is home. Not all chemical oases at the bottom of the Pacific are hot. Some are cold seeps, places where methane, sulfide, and other chemicals seep from the sediment into the ocean. The water is not boiling. There may be no chimney, no black plume, no towering mineral architecture. The signs can be subtler. Pale mats of bacteria, clusters of clams, tube worms standing in the mud, carbonate rocks formed by microbial activity, shimmering traces of fluid escape. Cold seeps are slower in feeling than vents. They can last longer. They may be associated with continental margins, subduction zones, mud volcanoes, and places where buried organic matter is transformed into methane. Like vents, they support chemosynthetic life. Microbes use chemical energy. Animals partner with them. Communities form around what leaks from the earth. In the Pacific, where plates meet and one slab dives beneath another, seeps can occur along margins shaped by compression and earthquake. The sea floor there is not merely a floor, it is a seam. The animals at seeps often seem quieter than those at vents, less crowded into violent gradients, more spread along the sediment. Clams may sit partly buried, their shells open slightly. Mussels cluster in dark masses. Tube worms extend upward, red tips exposed. Bacterial mats spread like pale stains. A fish rests beside them, perhaps drawn by the concentration of life. The seep does not look like a miracle all at once. It looks like the seafloor has begun to breathe. For decades, the deepest trenches were assumed to depend mostly on food falling from above. That is still a crucial part of hadal life. Trenches collect organic matter like long, narrow basins. Landslides, currents, and the shape of the seafloor can funnel material downward. But the old picture has grown stranger. In the Northwest Pacific, scientists have documented chemosynthesis-based communities at extraordinary depths, including parts of the Kuril-Kamchatka and Aleutian trenches, where tube worms and bivalves live thousands of meters down, in places once imagined too remote for such ecosystems. This is not a small adjustment. It means that even the deepest parts of the ocean may hold local sources of chemical energy. It means trenches are not only endings where debris gathers, they can also be openings. The hadal zone begins around 6,000 meters and extends into the deepest trenches. The name comes from Hades, the underworld, but the name can mislead. It suggests a single realm of death. In reality, each trench is its own landscape, shaped by tectonics, sediment, chemistry, and food supply. Some are narrow, some are steep, some are geologically active. Some receive more organic matter than others. The Pacific holds most of Earth's hadal environments, a ring and scattering of deep cuts around its edges and island arcs. The Mariana Trench is the most famous because it contains Challenger Deep, the deepest known point in the ocean. But it is not the only trench, nor the only hadal world. The Tonga Trench, Kermadec Trench, Japan Trench, Kuril-Kamchatka Trench, Aleutian Trench, Philippine Trench, and others form a broken geography of extremes. To descend into a trench is to leave the abyss and enter a steeper kind of darkness. The walls rise, sediment slumps. Earthquakes can rearrange the bottom. Organic material can collect in pockets. The pressure climbs beyond what most life on Earth will ever experience. At 10,000 meters, it is about 1,000 times the pressure at sea level. Every square centimeter is under enormous force. A machine must be designed almost like a spacecraft in reverse, built not to hold pressure in, but to keep pressure out. And yet, the animals are there. Hadal amphipods, isopods, sea cucumbers, polychaete worms, bivalves, microbes in sediment and water, snailfish in some trenches down to record depths, their soft bodies adapted to pressure, their bones reduced, their tissues carrying chemistry that helps life continue near the edge of what fish can endure. Below them, where fish seem unable to go, invertebrates continue. The hadal seafloor can look pale and soft, but it is not simple. A trench is a collector of histories. Ash falls from eruptions. Landslides carry material from slopes. Dead organisms sink. Microbial processes continue in buried layers. The chemistry of the sediment changes with depth. Life makes use of what arrives and what seeps upward. A baited lander reaches the bottom and waits. For a while, there is only the circle of light on the sediment. Then one amphipod enters, then another, then dozens. Their bodies flick and fold. They arrive from nowhere, responding to the smell of food in a black ocean. The camera records them in a brightness that does not belong to their world. Beyond the beam, the trench remains as it was before, dark, cold, immense. The animal life at the bottom of the Pacific often appears delicate, but delicacy here is misleading. A snailfish from a trench may look translucent and soft, almost unfinished, with a broad head and small eyes. It is not armored. It does not need the heavy bones and scales of a surface predator. In its world, flexibility is strength. A rigid, gas-filled body would be a liability. Softness is not weakness. It is a solution. Some deep animals have reduced eyes. Some have no need for vision in the ordinary sense. Some sense pressure waves, chemicals, vibrations, faint glows. The darkness is not empty to them. It is textured with information humans cannot easily imagine. A fish near the seafloor may rest motionless for long periods, conserving energy. A predator may drift rather than chase. A scavenger may carry a sense of smell tuned to rarity. A worm may feed through sediment steadily, unheroically, doing the work that keeps the bottom from becoming only accumulation. The deep Pacific does not reward wastefulness. Bodies are shaped by thrift. But it also produces extravagance of form. Glass sponges with lattice skeletons, sea pigs moving on swollen tube feet, basket stars unfurling branching arms, Dumbo octopuses hovering with ear-like fins, big-fin squid with arms trailing like impossibly long threads, siphonophores that look less like animals than drifting sentences written in light. The farther humans look, the less the deep sea resembles the barren place we expected. The bottom is not crowded everywhere, but it is imaginative everywhere. One of the reasons it has remained mysterious is that humans are poor witnesses at depth. We arrive with lights, noise, metal, thrusters, bait, and limited time. Our cameras show circles, not worlds. Our samples tear small pieces from vast systems. Our presence changes behavior. Some animals flee from light, others are attracted. Some are too small to notice. Some live inside sediment. Some exist in chemical gradients that collapse when removed. To know the bottom of the Pacific, humans must build machines that can endure what humans cannot. ROVs descend on cables, carrying cameras, arms, sampling tools, sensors. A ship above holds their lifeline, rolling on waves thousands of meters over the worksite. Pilots sit in control rooms, hands on joysticks, watching screens where the bottom appears in artificial light. A manipulator arm reaches toward a sponge as carefully as fingers reaching toward a glass ornament. Sediment puffs. A crab backs away. A scientist leans closer to the monitor, seeing an animal no one may have seen before. Autonomous vehicles map the seafloor without a cable, flying pre-planned paths through darkness. Landers drop from ships and fall for hours, carrying bait, cameras, traps, acoustic releases. Human-occupied submersibles descend more rarely, their occupants sealed inside pressure spheres, looking out through small windows at a world that seems not to care that they have arrived. Every dive is brief compared to the deep ocean's time. A submersible reaches the bottom after hours of descent. It has battery limits, oxygen limits, communication limits, weather limits from the surface world. The people inside may have only a few hours to look. Outside, the seafloor has had millions of years. There is humility built into deep-sea exploration, if one pays attention. The Pacific does not reveal itself as a map all at once. It reveals itself as glimpses. A vent chimney, a field of nodules, a trench wall, a fish at the edge of the light, a plastic bag where no plastic bag should ever be, a beer bottle on the deepest floor, a new species in a sample jar, a sound recorded at Challenger Deep, earthquakes, storms, distant ships, the calls of whales traveling through layers of water. Even at the bottom, the human world arrives, not as cities, not as footsteps, but as signals and debris. Microplastics have been found in deep marine environments. Chemical pollutants can travel through food webs. Fishing gear can sink. Litter can descend. The idea that the deep ocean is safely separate from us has become harder to defend. The bottom of the Pacific is remote, but it is not protected by remoteness. Everything sinks eventually, or almost everything. Carbon sinks, bodies sink, ash sinks, dust sinks, waste sinks. The deep sea receives the consequences of the surface with a patience that can be mistaken for permission. Yet the bottom is not passive. It stores carbon. It recycles nutrients. It supports biodiversity. It influences the long chemistry of the ocean. It connects to climate in ways that are still being understood. Deep currents carry water masses around the planet over centuries. Organic matter buried in sediment becomes part of Earth's carbon story. Microbes in the seabed participate in cycles that shape ocean chemistry. The bottom of the Pacific is not scenery beneath the real ocean. It is one of the real ocean's foundations. Imagine a single particle of marine snow. It begins as part of a phytoplankton cell in the sunlit surface, perhaps somewhere in the central Pacific where the water is blue because it holds so little suspended matter. The cell lives briefly. It divides. It is eaten by a tiny grazer. Part of it becomes waste. The waste pellet sinks, gathering bacteria, fragments, other particles. It falls out of the bright world. At 500 meters, it passes animals rising and descending in the daily migration. Some particles are eaten here, others continue. At 1,000 meters, the cold increases. At 2,000, the particle is still falling, smaller now, altered by microbes and nibbling mouths. By the time it reaches the abyssal floor, it may be only a trace of what it was. But a trace is enough for something. A deposit-feeding animal takes it in with sediment. A microbe breaks it down. A worm moves the mud. The carbon that once floated in sunlight becomes part of a body in darkness, or becomes dissolved, or is buried. The surface and the bottom have touched, but slowly, through a long, vertical economy. This is the ordinary miracle of the deep sea, the living rain. But sometimes, the rain becomes a storm. A bloom at the surface can send a pulse of food downward. A massive die-off can feed the seafloor. A dead whale can transform a plane. A woodfall can carry land into the abyss, bringing cellulose and shelter to animals adapted to rare gifts. Even a coconut, drifting and sinking, can become a small island of matter. The Pacific bottom is not equally hungry everywhere. Some regions receive more food from productive surface waters. Others lie beneath vast oligotrophic zones, where the surface itself is sparse. The deep reflects the sky above it in ways that are not visible from the surface. Where productivity blooms, more can fall. Where currents carry, more can collect. Where trenches funnel sediment, food may be concentrated. Where plains lie under blue deserts, life may become especially thin and patient. The sun does not reach the abyss, but the pattern of sunlight still matters. A creature at the bottom may be living on weather it never felt, on storms it never heard, on blooms it never saw. The great Pacific gyres turn above, enormous systems of current and wind. Beneath them, water masses move in slower architectures. Cold, deep water carries oxygen into the abyss. Without oxygen, many animals could not live there, even if food arrived. The deep ocean is dark, but not dead, partly because surface waters in polar and subpolar regions sink after cooling, carrying dissolved gases into the interior. The breath of the deep can begin far away. The bottom of the Pacific is therefore connected not only upward, but sideways across the planet. A change in climate, circulation, oxygen, surface productivity, or chemistry can eventually reach it. Slowly, perhaps, unevenly. But the deep is not outside change. It is simply where change takes its time arriving, and where recovery may take even longer. In some areas, oxygen becomes low. In others, currents bring enough for animals to persist. The distribution of oxygen helps shape where certain species can live, how active they can be, how large communities become. Deep sea life is not only a battle against darkness and pressure. It is a negotiation with food, oxygen, substrate, chemistry, disturbance, and time. When the camera crosses the abyss, it may catch a fish suspended just above the bottom. The fish is not colorful in the way reef fish are colorful. Its body may be brown, gray, translucent, violet, or pale. In the artificial light, it seems revealed unfairly, pulled out of its own invisibility. It hovers with minimal motion, conserving itself. Its eyes, if large, gather faint traces. If small, they suggest another way of knowing. A rat-tail fish moves with a long, tapering body, its head broad, its tail narrowing into a thread. It searches the sediment for food. It is a common figure in the deep, but common does not mean ordinary. To live where meals are sparse, to mature slowly, to find mates in a landscape without landmarks, to endure pressure and cold and darkness, this is a form of mastery. The deep sea often makes human categories seem childish. Ugly, beautiful, primitive, advanced. These words fail quickly. A hagfish feeding at a carcass may repel us, then fascinate us, then become beautiful in the logic of what it does. A sea cucumber may seem ridiculous, then essential. A tube worm may look like a plant, then become a lesson in symbiosis. A microbe may be invisible, then turn out to support an entire community. The bottom changes what importance looks like. A bacterial gnat may be more consequential than a predator. A worm may be an engineer. A particle may be a feast. A crack in stone may become a garden. The Pacific is often described by its surface moods: calm, stormy, blue, dangerous, vast. But the bottom has moods too, though they are harder to name. There is the stillness of abyssal mud, the shimmering unease of hydrothermal vents, the pale quiet of cold seeps, the steep compression of trenches, the eerie elegance of seamount slopes, the dust-filled darkness beneath a vehicle's thrusters, the sudden intimacy of seeing an animal turn toward a camera in a place where no human eye belongs. The cold open of the deep ocean never really ends. Every glimpse creates another question. Why here? How long has this animal lived? Where did its larva come from? What does darkness mean to a creature that has never known light? How much life is hidden in the sediment beyond the reach of the beam? How many species have lived and died at the bottom of the Pacific without ever being seen? The answers come slowly, and sometimes the answers are only better questions. The Challenger Deep sits in the western Pacific in the Mariana Trench, nearly 11 kilometers below the surface. It is often described with comparisons because the depth itself resists imagination. Mount Everest could be placed inside and still be submerged. The pressure is more than 1,000 atmospheres. The descent of a human-occupied craft takes hours. The ocean above is not just water. It is weight, distance, isolation. But comparisons can make it sound like a stunt, a record, a trophy depth. The deepest point becomes a number, and the number becomes the story. Yet, the bottom of Challenger Deep is not important only because it is deepest. It matters because it reminds us that Earth still contains places where arrival is rare, where direct observation is fragmentary, where life is not absent, but difficult to understand. When the bathyscaphe Trieste reached the Challenger Deep in 1960, Jacques Piccard and Don Walsh spent only a short time on the bottom. Their descent was historic, but their view was limited. They saw sediment. They reported signs of life, though later interpretations of some observations became cautious. The important fact remains that humans had physically entered the deepest known place and found not a mythic abyss, but a real seafloor. A place, not an idea. Decades passed before another human returned. Technology advanced. Robotic vehicles reached depths once impossible. James Cameron descended in 2012. Victor Vescovo and others later made repeated full ocean depth dives. Each mission brought better sensors, cameras, sampling, mapping. Each also showed how little a descent can cover. A submersible at the bottom of Challenger Deep explores a patch. The trench extends far beyond the patch. The Hadal world extends far beyond one trench. The deepest ocean is both reached and unreached. At full ocean depth, design becomes philosophy in metal. A submersible must be small enough, strong enough, simple enough in the right places. Its windows cannot be large and cinematic. Its sphere cannot compromise. Every seal matters. Every material behaves under pressure. The craft descends through black water, with no possibility of rescue in the ordinary sense. Above, the ship waits in weather. Below, the pilot and observers listen to creaks, instruments, the steady knowledge that the ocean is testing every assumption. The machine's lights finally strike bottom. Sediment, a slope, a faint movement. The deepest point on Earth does not greet visitors with spectacle on command. It may appear plain, and that plainness is part of its power. We expect the ultimate depth to look ultimate, to display itself with cliffs and monsters and revelations. Instead, the deepest place may show mud, small animals, scattered debris, and the quiet fact of existence under impossible pressure. The abyss does not perform. it persists. Some of the most important life there is microbial. In hadal sediments, microbes process organic matter that has fallen or been transported into trenches. They participate in nitrogen, sulfur, carbon, and methane cycles. The high pressure affects them, but they have adapted in ways scientists are still working to understand. Their enzymes function, their membranes remain usable, their metabolisms continue. Microbes are often treated as background, yet in the deep ocean, they are the continuity beneath everything. They colonize particles as they sink. They cover surfaces. They live in sediments. They form mats at seeps and vents. They enter symbioses with animals. They turn chemistry into food. They make the deep sea floor biologically possible. To tell the story of life at the bottom of the Pacific without microbes would be like telling the story of a forest without mentioning leaves. At hydrothermal vents, microbes may be the first settlers. At cold seeps, they form visible white, orange, or gray mats. In whale falls, they transform bones into chemical energy. In abyssal mud, they work at low concentrations, slow rates, subtle gradients. Some live below the seafloor, in cracks and pores, in the sub-seafloor biosphere, where life may extend into rock and sediment far deeper than once expected. The bottom is not a surface only. It has depth beneath depth. Beneath the mud, chemical conditions change. Oxygen may vanish in upper layers. Other metabolisms take over. Sulfate reduction, methanogenesis, anaerobic processes. The vocabulary becomes technical because the life becomes chemically intricate. But the image is simple. Beneath the visible seafloor, hidden communities persist, without eyes, without light, without drama, using the faint possibilities left in matter. A handful of sediment from the abyss can contain a world. Not a world that would impress us visually, perhaps. No bright movement, no face, no immediate story. But under microscopes and genetic tools, it opens into diversity. The deep Pacific is filled with life that cannot be filmed in the usual way, life that cannot be narrated by shape alone. To understand it, humans must read chemistry, DNA, isotopes, pressure experiments, slow incubations, patterns of metabolism. The cinematic image of the deep sea is often a light moving over darkness, but much of the real cinema is invisible. It is a molecule passing through a cell membrane, an enzyme holding its form under pressure, a bacterium using sulfide, a microbe dividing after a long interval, a gene carried through a population hidden in mud, a faint pulse of chemical energy moving from rock to cell to animal. Life at the bottom of the Pacific is not only what the camera can love. The Pacific plate itself moves beneath all of this, carrying the seafloor like a conveyor through geological time. New crust forms at spreading centers. It cools, sediment accumulates. Seamounts ride along. Eventually, at subduction zones, old oceanic crust bends downward into trenches. The seafloor that held abyssal life may be dragged toward the mantle. The bottom is not permanent, even if it seems eternal from the perspective of a human life. A grain of sediment may lie undisturbed for ages, but the plate beneath it is traveling. At trenches, this motion becomes visible in shape. One plate dives beneath another, forming deep arcs, earthquakes, volcanoes, deformation. The Pacific's margins are ringed with this tectonic drama. The same forces that make trenches also feed volcanic arcs and reshape continents. The bottom of the ocean is not separate from mountains. It is part of the same planetary restlessness. In a trench, geology can feed biology directly and indirectly. Fractures allow fluids to move. Organic matter accumulates. Methane may seep. Earthquakes can trigger slides that deliver food or bury communities. The walls and floor of a trench are not static. They are active landscapes where life must adapt to both scarcity and disturbance. A hadal animal may live in a place that feels timeless until the slope fails. Then, sediment moves like weather. The deep ocean has storms of its own. Not storms of wind and rain, but turbidity currents, sediment flows, benthic storms, pulses of organic matter, volcanic eruptions, hydrothermal shifts, oxygen changes. The surface ocean's violence is visible. The deep ocean's violence is often discovered later by broken cables, buried instruments, altered maps, communities erased and replaced. Even quiet places have events. The abyssal plain, too, may be disturbed by currents that sweep near the bottom, shaping ripples and redistributing particles. It may receive ash from distant eruptions. It may be crossed by animals whose tracks remain. It may be altered by human equipment. Its stillness is relative, not absolute. But relative stillness matters. Slow environments often create slow lives. Many deep-sea animals grow and reproduce at rates that make them vulnerable to sudden change. Deep-sea corals can live for centuries or longer. Some sponges and invertebrate communities may take long periods to establish. A trawl, a mining machine, or a plume of sediment can alter habitats faster than they can recover. At the bottom of the Pacific, damage can outlive memory. A person may not remember a track made decades ago. The seafloor may. This is why the idea of mining the deep Pacific has become so charged. Polymetallic nodules contain metals used in batteries and electronics. Supporters argue that society needs these materials and that deep-sea mining may reduce impacts elsewhere. Critics warn that the abyssal ecosystems are poorly understood, slow to recover, and vulnerable to sediment plumes, noise, light, and habitat removal. The debate is not only economic, it is moral, scientific, and temporal. How much should humans take from a place we barely know? How do we measure loss in an ecosystem where many species are undescribed? What does restoration mean when the habitat grows over millions of years? The bottom of the Pacific forces a different kind of accounting. On land, destruction is often visible. A forest becomes a clearing. A river changes color. A mountain is cut. In the abyss, damage may happen beyond sight, beyond public imagination, beneath international waters, in a place most people will never picture clearly. The invisibility of the deep can become its danger, but the deep ocean is not valuable only because it might be useful or vulnerable. It is valuable because it exists, because life has found ways to inhabit it, because Earth is deeper and more complex than human convenience. There is a kind of arrogance in thinking darkness means emptiness. The seafloor has been correcting that assumption for more than a century. Long before cameras, sailors lowered weighted lines to measure depth. Sounding the ocean was slow, uncertain work. A line descended through water, sometimes for hours. When it touched bottom, if it touched bottom, it brought back a number, maybe a bit of mud, maybe a clue. The ocean floor entered human knowledge as scattered points. The HMS Challenger expedition in the 1870s transformed that knowledge. It crossed the oceans, measured depths, collected samples, documented marine life, and helped lay foundations for oceanography. In the Pacific, its soundings revealed extreme depths and hinted at the scale of hidden terrain. Yet even then, the deep was known mostly by absence. A line could say how far down the bottom was. It could not show what life there was doing. Later, sonar began turning depth into shape. Echoes returned from the seafloor. Maps improved. Ridges, trenches, plains, and seamounts emerged. Satellites inferred seafloor features from subtle changes in sea surface height caused by gravity. Multi-beam sonar added detail. But mapping is not seeing. A map can show a mountain no camera has visited. It can trace a trench whose animals remain unknown. The Pacific bottom is still incompletely mapped at high resolution. There are places on the Moon and Mars that are better imaged than parts of Earth's own seafloor. This comparison is often repeated because it is startling, but the real meaning is quieter. The deep ocean is difficult not because it is far in miles, but because it is hostile to easy presence. Water absorbs light and radio signals. Pressure destroys ordinary equipment. Salt corrodes. Weather interrupts ships. Time at sea is expensive. The bottom resists convenience. Exploration here is not one heroic moment. It is logistics, engineering, patience, funding, weather windows, broken parts, lost vehicles, uncertain samples, long nights on research vessels, scientists watching screens at 3 in the morning while a robot arm tries not to crush a fragile animal. The romance of the deep ocean is real, but it is built on work. A research vessel over the Pacific Abyss may look small beneath the sky. Inside, people move through narrow corridors, eat meals on schedules shaped by watches, sleep lightly when the ship rolls, label samples, check cables, troubleshoot software, argue over identification, celebrate when a camera lands upright, go quiet when a vehicle is lost. The bottom appears on screens, but the ship remains in the surface world. Weather reports, engine noise, coffee, wet decks, satellite messages from home. This human world and the Hadal world touch through a cable thinner than the scale of the ocean. The ROV descends for hours. Its tether trails upward into blackness. On screens, particles move past like stars. Then the seafloor arrives suddenly, a pale plane emerging from below. Everyone in the control room leans in, though they have seen it before. Arrival never becomes ordinary. The bottom is always a threshold. The first minutes are often practical. Check altitude, check thrusters, confirm position, avoid stirring sediment, begin transect, record, narrate observations, collect sample. But beneath the practical language is awe, restrained by procedure. A scientist says, "Possible holothurian at 2 o'clock." What they may feel is closer to, "Something is alive here, and we are seeing it now." The bottom of the Pacific is not only a scientific frontier, it is an emotional frontier, because it changes the scale of belonging. Humans evolved under air and light. We understand landscapes by walking, by horizon, by weather, by the behavior of flame and trees and animals we can touch. The deep sea floor offers almost none of that. It has no sky, no sunrise, no open flame, no scent in the human sense, no weather on the skin. It is Earth, but Earth stripped of most cues that make Earth feel familiar. And still, it is not alien enough to be separate. The water is the same ocean that touches beaches. The carbon falls from the same surface where dolphins breathe and ships pass. The tectonic plates connect to earthquakes and volcanoes. The oxygen comes from planetary circulation. The litter comes from human hands. The life is made from the same basic chemistry as ours. The deep Pacific is not elsewhere. It is below. That word changes everything. Below means connected. Below means receiving. Below means hidden, not absent. At a hydrothermal vent, a shrimp grazes bacterial film from rock. Its body lives in an environment of sharp gradients. Move too close to the hot fluid, and it dies. Move too far from the chemical flow, and it loses the microbial productivity that feeds the community. It lives in a narrow band of possibility. Much of life, everywhere, lives in such bands. Humans notice extremes when they are dramatic, but all life depends on limits. Temperature, pressure, pH, oxygen, salt, energy. The deep sea simply places those limits where we can see them in stark form. It reminds us that habitability is not a single condition, but a negotiation among many. At vents, the negotiation is intense. Animals position themselves carefully. Microbes occupy chemical layers. Heat-loving organisms may live within chimneys where conditions would kill most creatures. Others stay in cooler mixing zones. The entire community is arranged around invisible chemistry. To human eyes, it may look like a cluster of animals. To the animals, it is a map of flows. A black smoker is a fountain of Earth's interior meeting the ocean. The plume rises, cools, spreads, and carries minerals into the water. Some precipitate quickly, building the chimney. Some travel farther, influencing ocean chemistry. Vents are small compared to the size of the Pacific, but their significance is large. They move heat and chemicals from the crust into the ocean. They host life that altered our understanding of biology. They may resemble environments where early life on Earth found energy. The origin of life remains uncertain, but hydrothermal systems are part of many hypotheses because they bring together rock, water, heat, chemical gradients, and catalytic mineral surfaces. Whether life began in places like these is still debated. But standing, imaginatively, at a Pacific vent, watching animals thrive in darkness on chemical energy, it becomes easier to understand why such places matter to the deepest questions. Not every answer lies in the stars. Some lie under mud. Some lie in cracks of basalt beneath 6 kilometers of water. Some lie in bacterial metabolism at the edge of heat and cold. The deep sea has a way of turning the very old into the very immediate. A vent chimney may grow quickly in geological terms, but it is fed by processes rooted in plate tectonics. A nodule may sit exposed for millions of years, gathering metal atom by atom. A coral may record changes in ocean chemistry across centuries. Sediment layers may preserve traces of climate, extinction, volcanic eruptions, industrial pollution. The bottom is an archive, but not a dead one. It is an archive that eats, breathes, moves, and is moved. A core of abyssal sediment lifted to a ship can look unimpressive, a cylinder of mud, yet inside it are layers of time, microfossils, chemical signatures, ash horizons, organic carbon, clues to past productivity and circulation. Scientists split the core, photograph it, sample it, analyze it. The mud becomes a text written slowly by the ocean. Life writes in it too. Worms burrow, animals mix layers, microbes alter chemistry. Tracks appear on the surface. Fecal pellets become sediment. Shells dissolve or persist depending on depth and chemistry. The seafloor is not a page untouched by readers. It is being edited constantly by small bodies. At abyssal depths, calcium carbonate shells may dissolve if the water is undersaturated, leaving fewer hard remains. Silica from diatoms and radiolarians may persist in some areas. Clay may dominate. The composition of the bottom reflects the balance between what falls, what dissolves, what is transported, and what time allows. To an animal living there, this geology is not abstract. Mud texture affects burrowing. Hard substrate affects attachment. Chemical conditions affect microbes. Slopes affect food accumulation. A small change in terrain can change a life. The deep ocean is often described as monotonous because humans see little variation at first glance. But at the scale of its inhabitants, the abyss is full of differences. A pebble, a nodule, a burrow, a ripple. a carcass, a fecal mound, a bacterial patch, a sponge stalk, a slight current, a trace of odor. A desert is not empty to the animal that knows how to read it. Neither is the abyss. The Pacific bottom also contains sound. Not the dramatic soundtrack humans add later, but real vibration traveling through water. Sound moves well in the ocean, and the deep can carry signals over long distances. Whales call, earthquakes crack, ice can rumble far away. Ships produce low-frequency noise. Storms stir the surface and send energy downward. Hydrothermal activity may produce subtle acoustic signatures. Landslides and eruptions have voices. At Challenger Deep, instruments have recorded a surprising soundscape, natural and human-made sounds reaching even the deepest place. The idea of a silent abyss is not entirely true. It is dark, but not mute. For animals, sound and vibration may matter deeply. In darkness, pressure waves can reveal movement. Chemical cues can reveal food. Touch can map surfaces. Light, where it exists, may be self-made. The sensory world of the bottom is not a diminished version of ours. It is organized around different priorities. A sea cucumber does not need a horizon. An amphipod does not need sunrise. A vent mussel does not need seasons. A microbe does not need a face. The deep sea asks us to stop measuring life by resemblance to ourselves. This may be why it feels philosophical without trying. It shows life continuing in forms that do not flatter human intuition. It shows ecosystems without plants, food webs without sunlight at their base, at least locally, animals without eyes that still find what they need, communities built on poison, slow lives in cold mud, soft bodies under crushing pressure, fragile-looking organisms stronger than our machines in the one way that matters. They belong where they are.
The bottom of the Pacific is not inspirational in a simple way. It does not say that anything is possible. Many things are not possible. Fish likely cannot live below certain depths. Vent animals die when flows cease. Abyssal species may be devastated by disturbance. Pressure destroys unadapted life. Scarcity limits abundance. Chemistry sets boundaries. But within boundaries, life improvises. That is the deeper wonder. Not infinite possibility, specific possibility, found and inhabited. At a cold seep, tube worms may live for a very long time, their roots extending into sulfide-rich sediment while their plumes reach oxygenated water. They bridge chemical worlds. Their symbiotic bacteria turn that bridge into nourishment. The worm is an animal, a habitat, and a conduit. At a vent, a young community may grow after an eruption, colonists arriving through dark water. Larvae somehow locate new habitat. Some may respond to temperature, chemistry, microbial films, currents. The dispersal problem is immense. Vents can be separated by long distances, and suitable habitat may be patchy and temporary. Yet life connects them. The deep ocean contains hidden maps of dispersal. Currents carry larvae. Seamounts may act as stepping stones. Trenches may isolate populations. Plate boundaries may create chains of habitat. Genetic studies reveal relationships across distances that cameras alone cannot show. A species at one vent may be related to populations far away or unexpectedly distinct. The bottom is a geography of both connection and isolation. The Pacific is especially vast, and vastness affects evolution. Populations separated by depth, distance, chemistry, and currents may diverge. Endemism can be high in some deep-sea habitats. Many species remain undescribed. A single expedition can bring up animals that require years of taxonomic work.
The deep sea is not just unexplored space. It is unnamed life. Naming is not ownership, though it can be mistaken for it. To name a species is to admit it was there before the name. At times, the deep Pacific seems to resist narrative because its timescales are so unlike ours. A video clip shows a few minutes. A dive lasts hours. A research program may last years. But the seafloor changes over decades, centuries, millennia, millions of years. A nodule grows slower than a fingernail by absurd orders of magnitude. A sediment layer accumulates invisibly. A trench forms through tectonic motion. A vent field may flare and die within a human lifetime. Different clocks overlap. The script of the bottom is not one tempo. It is a chord of tempos. Fast microbes at vents, slow microbes in sediment, sudden landslides, patient plains, mobile scavengers, sessile sponges, drifting larvae, ancient crust, new lava, a falling carcass, a pressure wave from an earthquake, a plastic wrapper descending in a time almost insultingly brief. Human impact introduces a new tempo: fast, industrial, chemical, global. The deep ocean has never been frozen in perfection. It has always changed. But the speed and nature of human influence are different. Climate change can alter ocean temperature, oxygen, circulation, acidification, and food supply. Pollution can reach depths once assumed isolated. Noise can spread. Mining could disturb large areas before science fully understands them. Fisheries already impact deep habitats in some regions. The bottom of the Pacific is not beyond history anymore. Or perhaps it never was. Human history has simply become large enough to arrive there. On the abyssal plain, a sea pig walks. It is a type of sea cucumber, rounded, soft, with tube feet that look almost like legs. In footage, sea pigs can seem oddly charming, like small, inflated animals crossing the mud. Their appearance invites humor, and humor is not wrong. The deep sea is not solemn all the time. Some animals are strange in ways that feel playful to us. A Dumbo octopus flaps its fins like ears. A tripod fish stands above the seafloor on elongated fins. A barrel-eye fish looks upward through a transparent head. The deep contains absurdity alongside terror. But the sea pig is not a joke to itself. It is feeding, moving, reproducing, sensing. Its body is an answer to the seafloor. It processes sediment, redistributes material, becomes prey, leaves tracks. Its small passage matters at its own scale. The more one learns about the bottom, the harder it becomes to divide wonder into categories: beauty, function, weirdness, vulnerability, and scientific importance keep overlapping. The same animal can be comic, elegant, and ecologically serious. The same mud can be plain and full of life. The same darkness can be frightening and protective. A fish with reduced bones is not less complete. A worm with bacteria is not less independent in any meaningful human way. A microbe metabolizing slowly beneath sediment is not less alive because its drama is molecular. The deep ocean changes the emotional vocabulary of life. It asks for quieter attention. The bottom of the Pacific is also a place of edges. The edge between water and sediment. The edge between oxic and anoxic layers. The edge between hot vent fluid and cold seawater. The edge between tectonic plates. The edge between sunlight's influence and Earth's chemical energy. The edge between known and unknown. Edges are productive. They create gradients. They allow exchange. they concentrate difference. Life often gathers at edges because edges offer possibilities that uniform spaces do not. A vent is an edge. A seep is an edge. A whale fall is an edge between a dead surface animal and a living deep community. A seamount is an edge interrupting flow. A trench is an edge where the planet folds. Even the descent through the water column is an edge repeated. Surface to twilight. Twilight to midnight. Midnight to abyss. Abyss to hadal. The cold, open footprint in the mud is an edge too. It is the edge between absence and evidence. It says something passed here. It does not tell the whole story. It invites investigation. Much of deep-sea science begins with such traces. A trackway across the sediment may reveal movement where the animal is gone. A burrow may reveal life below the surface. A chemical anomaly may lead to a vent or seep. A temperature signal may indicate fluid flow. A DNA fragment in water may suggest organisms not directly observed. A sound may indicate activity beyond sight. A mineral deposit may reveal hydrothermal history. A damaged cable may reveal an underwater landslide. The deep ocean is read through clues. This makes it cinematic in a way that has nothing to do with exaggeration. It is naturally suspenseful because it withholds. The light moves forward. The next meter may be mud, or a new species, or a chimney, or a carcass, or nothing obvious at all. The mystery is honest. It comes from the limits of observation. There is no need to invent monsters. The real animals are stranger because they are true. A giant amphipod from the hadal zone, pale and curved, is not a monster. It is a scavenger adapted to pressure and darkness. Yet seeing it enlarged by the camera, arriving with others at bait in the deepest trench, one can feel the old human shiver. Something from below has come into the light. The shiver is not only fear, it is recognition that the world is bigger than our habits of thought. In the deep Pacific, scale repeatedly breaks expectation. The ocean is too wide, the depth too great, the animals too soft, the microbes too important, the mud too alive, the human machine too small, the footprint too meaningful. The bottom teaches through disproportions. A tiny particle feeds a tiny mouth. A tiny microbe supports a giant worm. A tiny variation in chemistry defines a community. A tiny human-made fragment reveals global impact. A tiny camera frame opens onto a planetary habitat. The abyssal plane may seem like a blank, but blanks can be powerful. They force attention onto subtlety. In a coral reef, the eye is overwhelmed. In the abyss, the eye learns to wait. After a while, the seafloor begins to show its marks. Faint trails, star-shaped traces, mounds, pits, animal positions, sediment textures. The emptiness becomes legible. This change in perception matters. Many human mistakes begin with failing to see. We look at a place and call it empty because it does not offer the kind of abundance we recognize. Grasslands were called empty. Deserts were called empty. Polar regions were called empty. Deep seas were called empty. The word often precedes extraction. The Pacific bottom is not empty. It is quiet. Those are different things. A quiet ecosystem can still be intricate. A sparse community can still be ancient. A low-energy environment can still be sensitive. A dark habitat can still be full of relationships. The bottom does not need to resemble a rainforest to deserve care. Still, there are places at the bottom that do resemble oases, and they are hard to forget. At a vent, the camera's lights strike a wall of life. Tube worms sway. White crabs pick their way across black rock. Bacterial gnats glow pale. Chimneys loom. The water shimmers from heat. It looks like a secret city built around a furnace. At a seep, clams cluster in sediment where methane rises. The mud may be stained white by bacteria. Fish hover nearby. Tube worms extend like slender reeds. The chemistry is quieter than a vent, but the concentration of life is unmistakable. At a whale fall, bones lie on the seafloor, first wrapped in scavengers, later colonized by worms and microbes. The skeleton becomes architecture. Rib bones become ridges. Vertebrae become islands. The whale's body, once a moving nation of muscle and breath, becomes a landscape. Each oasis reveals a different answer to the same question. Where does energy come from? From sunlight falling as debris. From Earth's interior rising as chemistry. From stored fat in bones. From methane in sediment. From the slow work of microbes. Life at the bottom of the Pacific is, in many ways, a study of energy after light. The sun still matters, but it is no longer sovereign everywhere. There is a humility in that. Humans live in a world visually dominated by sunlight. We wake by it, grow crops with it, build metaphors from it. Light means knowledge, hope, life. Darkness means ignorance, fear, death. The deep ocean does not obey those metaphors. Darkness there is not evil, it is simply the condition. Life has not waited for light to approve it. At vents and seeps, darkness is full of production. In abyssal mud, darkness is full of digestion. In trenches, darkness is full of adaptation. This does not make darkness comforting exactly. It remains vast and difficult, but it makes it less simple. The bottom of the Pacific is a place where human symbolism breaks down, and that breakdown is useful. It allows the world to be itself again. The cold at the bottom is another condition often misunderstood. Near freezing water suggests dormancy, but cold does not mean lifeless. It slows reactions, shapes metabolism, preserves, constrains. Animals adapted to cold may have membranes and enzymes suited to it. They may grow slowly, live long, move economically. In polar-influenced deep waters, cold is part of stability. But vents complicate cold with heat. A vent field can contain extreme thermal gradients, and animals exploit narrow ranges. Some microbes tolerate high temperatures, others live in cooler mixing zones. The presence of heat in the cold deep sea creates not comfort, but complexity. Temperature is not a single number down there, it is a landscape. Pressure is also a landscape, increasing with depth, defining zones, affecting who can go where. The hadal trenches are not simply deeper abyssal plains. Their pressure regimes create biological filters. Species adapted to 4,000 meters may not survive at 9,000. Hadal communities can be distinct, with organisms specially adapted to trench conditions. This vertical separation means the ocean is layered not only physically, but evolutionarily. Depth can isolate. A species may occupy a band, another may replace it below. Food falls through all layers, but animals do not move freely across them. Even the same seafloor distance can become enormous if depth changes sharply. A trench wall is not just a slope, it is a transition between pressure worlds. The animals living along it may occupy different depth ranges like neighborhoods stacked in darkness. Scientists sample these ranges with landers, trawls, cameras, environmental DNA, sediment cores. Each method sees differently and misses differently. Trawls can collect animals but damage bodies and habitats. Cameras observe behavior, but only within light. DNA detects traces, but may not show form or abundance clearly. Landers attract scavengers, but bias toward animals drawn to bait. Sediment cores reveal microbes and myofauna, but only in small volumes. Knowledge of the deep sea is assembled from imperfect instruments. This makes certainty careful. The script of the bottom should not pretend humans know everything. We do not. Even basic questions remain open in many regions. How many species live there? How they disperse? How communities recover? How climate change will alter food supply? How mining plumes behave? How microbial processes scale across basins? How hadal ecosystems differ from trench to trench? The unknown is not a decorative fog around the facts, it is part of the facts. At the same time, ignorance should not be used as an excuse for fantasy. The deep is mysterious enough without invention. The animals are real. The chemistry is real. The risks are real. The limits of knowledge are real. A good story about the bottom of the Pacific does not need to turn it into myth. It needs to let reality become strange at its own pace. That pace is slow. A camera drifts over mud. A small animal lifts its feeding arms. A white particle falls. A shadow crosses the beam. Nothing happens for several seconds. Then the viewer realizes that nothing happening is part of what is happening. The deep sea teaches a different kind of attention because its dramas are often small, distributed, and slow. A reef dazzles immediately. A vent astonishes. But much of the bottom asks to be watched without demanding. The reward is not spectacle alone. It is intimacy with processes usually hidden by scale. A brittle star curls an arm. A worm withdraws. A sponge filters. A fish breathes. A track fades under falling sediment. These are not lesser events. They are how the abyss is alive. There are also violent moments, though humans rarely witness them directly. A whale carcass being torn by scavengers, a volcanic eruption covering a vent community in lava, a turbidity current rushing down a canyon, breaking cables and burying life, an earthquake shaking a trench, a predatory strike in darkness, a sudden fall of organic matter triggering a feeding frenzy. The bottom is not peaceful in the sentimental sense. It contains hunger, competition, death, disturbance. But because energy is limited, violence often appears measured, opportunistic, efficient. The deep does not waste motion on drama. A hagfish enters a carcass through an opening and feeds from within. It can produce slime in extraordinary quantities, clogging predators' gills, changing the texture of the encounter. It is ancient in design, disturbing to watch, perfectly suited to what it does. Around the carcass, amphipods swarm. Worms arrive. Microbes bloom. The body disappears into many bodies. Death at the bottom is not an ending. It is a redistribution. The Pacific's deepest life depends on such redistributions, and this dependence gives the seafloor a certain melancholy. Much of what feeds it is fallen, snow of dead plankton, bodies of fish, whale bones, wood from drowned trees, ash, waste. The bottom is where the upper world is received after transformation. But melancholy is only one human reading. To the scavengers, a fall is not sorrow, it is opportunity. To microbes, it is chemistry. To sediment, it is layer. To the ocean, it is cycle. The deep does not share our categories of tragedy and renewal. It performs both without naming either. In the Pacific, there are also places where human history lies on the seafloor in more recognizable forms. Shipwrecks, aircraft, cables, lost instruments, wartime debris. Some become artificial reefs, some corrode in darkness, some release pollutants, Some are archaeological sites. The bottom holds not only natural history, but memory. A wreck in deep water can be eerily preserved compared to shallow sites. Cold, darkness, and low oxygen in some environments slow decay. But nothing is exempt from the ocean. Metal rusts. Wood is consumed by specialized organisms. Sediment gathers. Animals colonize. Human objects become substrates, hazards, shelters, ruins. The Pacific has taken fleets, aircraft, cargo, messages, machines, and bodies. At depth, history becomes quiet. A camera moving over a wreck may reveal a fish resting beside a gun mount, coral growing from a railing, sediment inside a room where air once was. The object remains human in shape, but the sea has begun translating it. The bottom does not preserve things as memorials, it incorporates them. This incorporation can be beautiful or troubling. A bottle becomes habitat for a small octopus, perhaps. A plastic bag becomes evidence of contamination. A cable becomes substrate. A lost trap continues fishing. The ocean does not distinguish intention. It responds materially. This is one reason the deep sea unsettles human pride. We imagine remoteness as escape from consequence, but the ocean is a system of connections. What enters it may travel, sink, fragment, dissolve, bioaccumulate, or persist. The bottom is not beyond the reach of human action. It is downstream of it. Even the carbon dioxide released into the atmosphere touches the ocean. The sea absorbs heat and carbon. Chemistry changes. Acidification affects carbonate systems. Warming affects stratification and oxygen. Changes at the surface can alter the quantity and quality of food reaching the deep. The abyss may be slow to show response, but slow response is not no response. In a world changing quickly, the deep Pacific becomes both witness and participant. It stores signals of change in sediment and coral skeletons. It receives altered flows of carbon. It holds ecosystems whose resilience we do not fully know. It asks whether humans can care about places they will never see directly. The answer is not guaranteed. Care often begins with image. A whale, a coral reef, a forest, a polar bear. The abyss resists iconic simplicity. Its animals can be strange, small, pale, dispersed. Its landscapes can look empty. Its processes require explanation. But perhaps this is why it matters. It challenges care to mature beyond charisma. Can we care for mud? For microbes? For a nodule field? For a sponge on a rock 5,000 meters down? For a trench community known from a few dives? For a creature not yet named? The bottom of the Pacific expands the moral imagination by asking it to operate without easy rewards. There is no sunset there, no bird song, no familiar face, only life continuing. A deep-sea coral growing on a seamount may be older than many nations. Its skeleton records chemistry from water masses that moved through the Pacific across centuries. Fish may shelter among its branches. Brittle stars may climb it. Sediment may gather around its base. A trawl could break it in moments. Time is stored in bodies at the bottom. This is one of the most difficult truths for modern humans who are skilled at speed. We can break what took centuries to grow, disturb what took millennia to settle, remove what took millions of years to form. The mismatch between human action and deep-sea time is perhaps the central ethical problem of the abyss. A manganese nodule may grow by millimeters over 1 million years. A mining collector could remove it in seconds. A community may establish slowly around hard substrate. A sediment plume could smother it before it is described. A trench ecosystem may be discovered in 2025 and threatened by decisions made before its ecology is understood. Discovery and disturbance now move almost together. The bottom is being revealed at the same moment it is being considered for extraction. This does not mean humans must never use the ocean. Humanity has always depended on seas for food, travel, climate, imagination. But dependence without humility becomes appetite. The deep Pacific is not an infinite warehouse. It is a set of living systems with histories and limits. Humility begins with looking carefully. In a control room, a camera hovers over a nodule field. The nodules dot the sediment like dark moons. Between them are tracks, burrows, tiny animals. A sponge grows from one nodule, raising itself into the current. It may be small enough to overlook, but for that sponge, the nodule is the world's anchor. The machine's light passes on. The sponge remains in darkness. Some of the most moving moments in deep-sea footage are not spectacular. A Dumbo octopus lifts from the seafloor and hovers, fins moving gently. Its arms webbed, its body soft, it seems almost weightless. It is not in a hurry. It crosses the beam and vanishes into black water. For a few seconds, the deep seems less like an abyss than a room into which an animal has quietly entered and left. Or a squid appears, long arms trailing at strange angles, holding a posture that seems impossible. It does not behave like the fast, muscular squids of surface imagination. It hangs in the water, a living geometry. Or a jelly drifts near the bottom, transparent except for internal lines, its body catching the light like glass. It pulses once, and the motion travels through it like thought. These animals are not necessarily at the seafloor all the time, but they belong to the deep ocean's lower world, the water just above the bottom, the benthopelagic realm. The boundary between seafloor and water column is not hard. Many animals move between them. Food falls through one to reach the other. Currents connect them. Predators hunt near the interface. Larvae rise and drift. Scavengers smell from above. The bottom of the Pacific includes the water just above it, a dark space where bodies hover, wait, and pass. A lander on the seafloor sees only those who come near. Beyond its lights, an enormous volume of water remains unobserved. Animals may be moving there constantly, faintly, in patterns we barely understand. Some avoid lights, some approach bait, some pass too quickly. Some are transparent enough to disappear. The deep ocean is full of near misses in observation. A species may pass outside the beam forever. This is why new discoveries continue, not necessarily because the life is rare, but because our looking is rare. A vast habitat sampled by tiny windows will always surprise us. The Pacific bottom may hold many common animals that remain unknown simply because no camera has crossed their range. Rarity in the deep sea can be partly an artifact of human absence. But true rarity exists too. Specialized vent species limited to certain regions, animals dependent on whale falls or seeps, populations isolated by trenches, slow-growing organisms with sparse distributions. The challenge is knowing which is which before harm occurs. Science advances by reducing uncertainty, but policy often demands decisions before uncertainty is gone. The bottom of the Pacific sits inside that tension. We want minerals, knowledge, protection, economic development, climate solutions, technological achievement. The deep offers and withholds. It promises resources and reveals vulnerability. It invites exploration and punishes carelessness. The ocean is not a moral teacher in itself, but attention to it can become one. At the bottom, the human sense of centrality weakens. There is no sign that this world exists for us. Most of its history unfolded without us. Most of its species do not know us. Its processes began before our ancestors stood upright and will continue after our machines fail. Yet our influence has reached it. This combination, irrelevance and responsibility, is difficult to hold. We are not central there, but we are consequential. A plastic fragment in a trench is not symbolically powerful because it dominates the ecosystem. It is powerful because it proves connection. It says the surface has arrived in the deepest place. It collapses the comforting distance between a human hand and Hadal mud. The same is true of pollutants found in deep animals, or microplastics in sediments, or noise reaching great depths. The deep ocean is not a sealed vault. It is a receiving body. What happens above becomes part of below. The Pacific has always been a receiver of rivers, dust, volcanic ash, falling organisms, meteor particles, continental erosion, ice age signals, warm periods, cold periods, migrations, extinctions. Human influence is another layer, but a rapid and pervasive one. The bottom will record us whether or not we intend to be recorded. Sediment is patient, but not forgiving in the way humans mean. It keeps evidence. A future core might show industrial metals, radionuclides, plastic-derived compounds, shifts in microfossils, changes in carbon. The deep seafloor may become one of the archives by which the Anthropocene is recognized. A layer of us, thin perhaps, but global. This thought can feel bleak. Yet the deep ocean also offers a counterweight to despair. Not optimism exactly, but perspective. Life there has endured darkness, pressure, scarcity, volcanic upheaval, tectonic burial, chemical extremes. It has diversified in ways humans are only beginning to see. Its existence is not fragile in the sense of being helpless. It is resilient within the conditions that shaped it. What is fragile is the fit between life and place when change becomes too fast or too large. Respecting the deep means distinguishing resilience from invulnerability. A vent community may recover from natural eruption because its species evolved with that disturbance, and larvae can recolonize. But a mining disturbance in a nodule field may remove habitat that does not regenerate on ecological timescales. A whale fall community may exploit temporary abundance, but that does not mean all deep-sea communities can absorb chronic pollution. A trench animal may survive immense pressure, but that does not mean it can survive chemical contamination or food web shifts. Strength in one dimension does not guarantee strength in another. The bottom's creatures are not superheroes. They are specialists. And specialists can be vulnerable when the world changes outside the range of their specialization. On the abyssal plane, the horizon does not exist in the visual sense. The light fades before distance can become landscape. The ROV's cameras create a moving bubble of visibility. The vehicle travels, and the world appears only as it enters the bubble, then disappears behind. This is how humans know much of the deep, not by standing in a place and looking outward, but by carrying a small circle of day through endless night. There is something intimate and tragic in that method. We see only what we illuminate, and our illumination is temporary. When the vehicle leaves, darkness returns immediately. The animals resume whatever darkness means to them. The track of the thrusters may remain. The memory remains only in data.
Deep sea footage can feel dreamlike because of this. The black background erases context. Animals seem to float in nowhere. Scale becomes uncertain. A small worm can look monumental. A large sponge can seem close until the vehicle approaches. Without sunlight, without horizon, without familiar objects, perception loosens. Scientists fight this with lasers that mark scale, sensors that record depth and temperature, navigation systems, sample labels, maps. Measurement anchors wonder, but wonder remains. A pair of red laser dots falls across a fish, and suddenly the creature has size. It is no longer a ghost. It is 20 centimeters long, at 4,300 meters, at a recorded temperature, on a known slope, during a specific dive. Precision does not reduce mystery. It gives mystery a location. The bottom of the Pacific is made of such located mysteries. A new species collected from a vent field, a microbial metabolism detected in trench sediment, a sound recorded at full ocean depth, a nodule field richer in animal diversity than expected, a seep community at 9,000 meters, a snailfish filmed deeper than any fish before it. Each discovery becomes a coordinate in the dark. The map fills slowly. Some animals at the bottom survive by becoming nearly invisible. Transparency helps in the water column, where light is faint or bioluminescent flashes might reveal outlines. On the seafloor, camouflage may mean matching mud, reducing contrast, remaining still. In the artificial glare of a submersible, these strategies fail temporarily. The animal is exposed to a kind of light that did not shape its evolution. This raises a strange question. What does the deep sea look like without us? Not black, perhaps, to animals that sense differently, not silent, not empty, not still. It is a world of chemical gradients, pressure fields, faint currents, vibrations, odors, textures, and occasional self-made light. Human footage is not the deep sea, as it is, but the deep sea translated into our visual language. Every documentary image from the abyss is an encounter between worlds, the animal's world and ours, darkness and light, pressure and engineering, patience and curiosity. The translation is imperfect, but it is enough to begin. A tripod fish stands above the bottom on elongated fin rays, facing into the current. It looks like a small instrument mounted on stilts. Its posture allows it to hold position and wait for prey drifting by. It does not roam dramatically. It lets the water deliver possibility. This strategy feels almost philosophical because humans often equate life with pursuit. But in the deep, waiting can be active. Stillness can be work. To hold position, to sense, to conserve, to strike only when needed. These are not passive acts. They are adaptations to a world where energy cannot be wasted. The deep sea honors patience because it demands it. A sponge filters patiently. A clam grows patiently. A microbe metabolizes patiently. Sediment accumulates patiently. A nodule forms patiently. Even exploration is patient. Years of planning for hours of bottom time, decades of study for partial understanding. The bottom of the Pacific is a rebuke to haste, and yet it is being drawn into a hasty age. This tension gives the modern deep ocean story much of its emotional force. We're discovering slowness while accelerating around it. We are learning how little we know while gaining power to disturb. We are naming species while considering extraction. We are marveling at vents while imagining other planets. We are finding trash in trenches while speaking of pristine wilderness. The story refuses purity.
the bottom is not untouched. It is not ruined. It is not fully known. It is not beyond reach. It is alive, connected, vulnerable, and vast. To live at the bottom of the Pacific is to exist without sunrise, but not without rhythm. The rhythms are different. Currents, falls of food, chemical flows, reproductive cycles, tectonic events, seasonal pulses from the surface translated downward. A surface bloom in spring may become a deep-sea meal weeks later. An earthquake may reshape a trench in minutes. A vent flow may shift overnight. A larva may drift for months. A coral may grow for centuries. The deep sea's calendar is written in arrivals. Food arrives. Larvae arrive. Lava arrives. Sediment arrives. Machines arrive. Sometimes nothing arrives for a long time. Absence itself becomes a condition. Animals adapted to the deep must be prepared for long intervals between opportunities. Scavengers can detect and exploit sudden food falls. Deposit feeders make do with low-quality sediment. Suspension feeders depend on currents. Symbiotic animals depend on chemical flows. Predators may have low metabolisms and flexible diets. Reproduction may require strategies for finding mates in sparse populations. Chemical cues, broadcast spawning, brooding, hermaphroditism in some groups, long-lived larvae. The details vary enormously, but the theme is consistent. Life must solve distance. Distance between meals, distance between habitats, distance between mates, distance between generations of discovery. The Pacific's size magnifies every problem. A larva released at a vent may be carried away from suitable habitat. A whale fall may be too isolated for some specialists, yet mobile scavengers find it. A seamount may rise like a stepping stone, but only for those able to use it. A trench may isolate populations in a long, deep valley. The bottom is not a continuous neighborhood. It is a mosaic of possibilities separated by enormous dark. Connectivity in the deep ocean is one of the central questions for conservation. If a habitat is disturbed, can larvae recolonize it from elsewhere? How far do species disperse? Are populations genetically connected or unique? How often do rare habitats occur? Which areas act as sources? Which are sinks? Without answers, protection can miss what matters. The bottom's vastness can deceive. It seems so large that any disturbance must be small. But if life depends on specific features, nodules, vents, seeps, seamounts, trench sediments, then the relevant habitat may not be vast in the same way. Remove the feature, and the species tied to it may have nowhere nearby to go. Scale protects some things and hides others. The deep Pacific is full of animals whose lives are tied to surfaces. A larva searching for a place to settle may need the right rock, the right chemistry, the right microbial film. A coral needs hard substrate and current. A sponge may need a nodule. A mussel needs seep or vent conditions. A tube worm needs access to sulfide and oxygen. The abyssal mud may look uniform, but even there, microhabitats matter. From a ship, the difference between one patch and another may seem negligible. From the perspective of a larva, it may be destiny. This is another reason the bottom resists simple storytelling. Its most important differences may be small, chemical, or hidden beneath sediment. A camera can miss them, a map can smooth them, a policy boundary can ignore them. Yet life organizes around them. The Pacific bottom is a reminder that reality is not obligated to be visible at the scale of human decision. We must learn to decide on behalf of things we cannot easily see. A white bacterial mat at a seep may look like a stain. In fact, it is a living surface of microbes using chemical energy. Animals graze it. It signals the flow of reduced compounds. It may indicate methane oxidation, sulfide production, or other processes, depending on the community. Its whiteness in the camera light is not emptiness, but metabolism made visible. A black smoker's plume may look like smoke, but it is mineral-rich fluid precipitating particles. It builds chimneys, it feeds microbes, it alters chemistry. It is the earth exhaling through seawater. A trench's mud may look like mud, but it may contain microbial communities processing carbon delivered from above and methane generated below. Its smoothness hides reaction. The deep sea repeatedly turns plain appearances into complex systems. This is why a voiceover about it must move slowly. Too much speed makes it sound like facts. But the bottom is not a list of facts. It is a place where facts accumulate into atmosphere. Depth, pressure, darkness, chemosynthesis, marine snow, vents, seeps, trenches, nodules, microbes. Each word is technical until it is allowed to become physical. Depth becomes hours of descent. Pressure becomes metal designed not to fail. Darkness becomes a fish without need of color. Chemosynthesis becomes a worm fed by bacteria in its own body. Marine snow becomes the surface falling. A vent becomes a city around a crack in the earth. A seep becomes the sea floor breathing. A trench becomes a valley deeper than mountains are high. A nodule becomes a stone that took longer to grow than humanity has existed. A microbe becomes the foundation of an ecosystem. Only then does the bottom begin to feel real. In one sense, the Pacific bottom is ancient. In another, parts of it are young. Oceanic crust is continually created and destroyed, so the seafloor is generally younger than continental rocks. At spreading centers, new basalt emerges. At subduction zones, old crust disappears. Sediment accumulates over that moving foundation. Life colonizes, adapts, disperses, and is carried across geologic conveyor belts. A vent field may be geologically young and biologically rich. An abyssal plain may rest on older crust under thick sediment. A trench may be a zone of destruction and concentration. The bottom is not a museum of stillness. It is a moving skin on a restless planet. This motion gives the Pacific its ring of fire, its trenches, island arcs, earthquakes, volcanoes, and hydrothermal systems. The same tectonics that threaten coastlines with earthquakes and tsunamis create deep habitats for chemosynthetic life. The planet's violence is also creative. At subduction zones, water locked in minerals and sediments is carried downward, influencing melting and volcanism. Fluids move. Methane can form. Seeps occur. The deep carbon cycle connects seafloor processes to the mantle and atmosphere over long timescales. Life participates in carbon cycling at the surface and in sediments. The ocean floor becomes part of planetary metabolism. It is tempting to separate biology and geology because our disciplines do. At the bottom of the Pacific, the separation is artificial. Rock feeds microbes. Microbes alter minerals. Animals depend on microbes. Sediment records life. Tectonics shapes habitats. Chemistry defines communities. Biology and geology are braided. A tube worm at a seep is not merely an animal. It is an expression of plate tectonics, microbial metabolism, ocean circulation, and evolutionary history, all gathered into one red-tipped body in black water. That is why the deep ocean can feel sacred without needing supernatural language. Its connections are already profound. At times, the bottom's mystery comes from how close it is. A person standing on a Pacific beach may be only hours by boat from water that drops into deep basins. The surface may be warm, bright, recreational. Children may play in waves. Farther offshore, the seafloor falls away, and eventually the same ocean becomes abyss. The transition is hidden by the surface. The beach and the trench are part of one body of water, but human experience divides them. The ocean's surface is a mask not because it deceives intentionally, but because humans cannot see through it. A calm day at sea can lie above thousands of meters of darkness. A storm can rage above animals that feel only distant changes. A whale can dive through layers, linking surface and depth in its own body. A dead whale can complete the link by sinking. Ships cross overhead, unaware of the communities below their roots. Satellites measure sea height, color, temperature, wind, while below, a snailfish moves through pressure no satellite can feel. The Pacific is vertical in a way human imagination often forgets. We map it as blue area, but the blue area has depth. Depth is not empty volume. It is habitat, history, process. If all the water were removed, the Pacific Basin would reveal a landscape more dramatic than most continents. Ridges longer than mountain chains, trenches deeper than any canyon on land, volcanic seamounts by the tens of thousands, plains wider than nations, fracture zones like scars, arcs of islands rooted in subduction, plateaus, basins, slopes. The bottom is hidden not because it lacks form, but because water conceals form. Human beings are visual animals. We believe what light gives us. The Pacific bottom asks us to believe in what darkness holds. Science helps by bringing back images, samples, maps, measurements. But imagination must do some work too. Not fantasy, but disciplined empathy for unseen places. To imagine the bottom accurately is to imagine pressure, not as crushing drama only, but as normal condition. To imagine darkness, not as void, but as habitat. To imagine cold, not as absence of life, but as a framework for different life. To imagine scarcity, not as failure, but as a set of strategies. To imagine mud, not as blankness, but as a living archive. The deep sea becomes less alien when we stop demanding that it resemble the surface. It becomes more alien too. Both are true. A hydrothermal vent community can vanish when the venting stops. Without chemical flow, the foundation collapses. The animals dependent on symbiotic bacteria lose their energy source. Sessile organisms die. Mobile animals leave if they can. The chimney remains, perhaps colonized differently, perhaps becoming a dead structure in darkness. This impermanence gives vent life an urgency. It must disperse, find, settle, grow, reproduce before the window closes. Vent species are often adapted to a patchy, shifting world. Their larvae may travel between sites. Their populations may boom and decline. The ecosystem can seem both ancient in concept and temporary in location. Abyssal nodule fields are the opposite in mood. Their defining structures grow incredibly slowly. The habitat may persist for millions of years. Disturbance there is not part of a rapid natural cycle in the same way. The animals are adapted to stability and low energy. This contrast matters. The deep sea is not one vulnerability profile. Different habitats have different histories of disturbance and recovery. A policy that treats the deep ocean as a single category will fail the details. Details are where life lives. In the Clarion-Clipperton Zone, studies have found high biodiversity, including many species new to science, in areas targeted for potential nodule mining. The animals may be small, but their diversity is not trivial. Some live in sediment, some attach to nodules, some move over the surface. Many are poorly known. The uncertainty is not a reason to assume low value. It is a reason to be careful.
The abyssal plain's visual quiet has long worked against it. A vent community looks obviously alive. A coral garden looks obviously vulnerable. A nodule field may look like stones on mud, but stones on mud can be habitat, and mud can be biodiverse. The deep teaches that obviousness is not a reliable measure of importance. A single ROV transect may reveal species after species unfamiliar to science. A sample may contain undescribed worms, crustaceans, mollusks, microbes. Taxonomists then begin slow work, comparing structures, sequencing genes, examining literature, determining whether an organism is truly new or newly encountered. The deep sea's biodiversity is not a spectacle of color alone. It is a hidden richness of forms, lineages, and functions. There is a quiet drama in a lab after an expedition, when the abyss is no longer a grand landscape on a screen, but a row of jars, vials, data files, images, and sediment cores. The bottom has been translated into evidence. The work continues under fluorescent lights, far from the ocean. A scientist examines a tiny worm under a microscope. Its bristles, jaws, segments, and tissues become clues. Another extracts DNA. Another measures isotopes. Another identifies mineral grains. Another models current patterns. The cinematic descent becomes months or years of analysis. Discovery is not finished when the vehicle returns. In many ways, it begins then. The reference image the public remembers may be a glowing vent chimney, but the scientific understanding comes from patient interpretation. The bottom is not self-explanatory. It must be studied across disciplines: biology, geology, chemistry, physics, engineering, computer science, taxonomy, climate science, policy. The deep ocean forces collaboration because no single lens is enough. This is fitting because life there is collaborative at its core. Symbiosis is one of the deep sea's great themes. Tube worms and bacteria, mussels and bacteria, clams and bacteria, microbes in sediments interacting across chemical gradients, animals hosting communities on their surfaces or in their tissues. Even whale falls become successions of species depending on the work of others. Life at the bottom is often life together in forms more intimate than human individuality comfortably imagines. A giant tube worm's body is a partnership so complete that the animal's anatomy has been reorganized around it. No mouth, no gut. A specialized organ full of bacteria, blood carrying sulfide and oxygen without poisoning itself. A plume reaching into the flow. The worm is a visible expression of microbial labor. This makes the old idea of independence seem less universal. At the bottom, dependence is not weakness, it is strategy. Humans, of course, are also symbiotic. Our bodies carry microbes. Our lives depend on other organisms, on plants, on ocean oxygen, on climate systems, on soil, on water. The deep sea does not invent interdependence. It reveals it in unfamiliar forms. Perhaps that is why vent communities feel so startling. They make visible a truth that is usually hidden. Life is built from relationships. Not all relationships are gentle. Predation, parasitism, competition, scavenging. But even these are connections. At the bottom of the Pacific, the food web is not a ladder, but a set of exchanges. Falling carbon, microbial transformation, chemical energy, scavenger pulses, sediment processing.
symbiotic production, predation, decomposition. Energy moves, changes form, becomes bodies, becomes waste, becomes sediment, becomes chemistry, becomes life again. The bottom is a place where transformation is slow enough to see if we learn how to look. A piece of wood sinking into the deep Pacific becomes colonized by wood-boring bivalves and microbes. On land, wood might rot in air, feed fungi, insects, soil. In the deep ocean, it becomes a rare package of energy and structure. Some animals specialize in such falls. The ocean takes a tree and makes a temporary deep-sea habitat from it. This is one of the more poetic connections between land and abyss. A forest grows in sunlight. A storm or river carries wood to the sea. It floats, waterlogs, sinks. It lands in darkness. There, animals that have never known a forest feed on it. The bottom receives the memory of land.
Rivers carry sediment, nutrients, pollutants, and organic matter to the ocean. Dust blows from deserts and settles on the sea, fertilizing plankton in some regions. Volcanic ash falls. Pollen can sink. Human-made particles travel. The deep Pacific is connected not only to marine life, but to continents and atmosphere. The abyss is planetary, not merely oceanic. This vast connectedness can be overwhelming, but the story returns, always, to small scenes. A worm in a tube, a fish in a trench, a sponge on a nodule, a microbe in mud, a footprint fading slowly. The bottom can only be emotionally understood through particulars. Otherwise, its scale becomes abstraction. 36,000 feet, millions of square kilometers, thousands of atmospheres, millions of years. These numbers are true, but they are too large to feel. A single animal crossing the sediment gives the scale a point of contact. The cold open footprint matters because it is small. It makes the abyss intimate. One of the most haunting facts about the deep sea is that many of its inhabitants may live and die without ever encountering solid light from the surface. Their only illumination may be bioluminescent flashes, faint glows from organisms, or the sudden artificial sunrise of a submersible. Imagine a fish whose ancestors have lived in darkness for millions of years, and then, one day, a machine descends, shining white beams across the mud. For the animal, if it perceives the light at all, it may be disturbance, threat, curiosity, nothing meaningful. For humans, it is revelation. This asymmetry is present in every deep-sea image. We are astonished. The animal is living. Our wonder is not the event itself. The event is the animal's ordinary life. A sea cucumber feeding on sediment does not know it is teaching us about the persistence of life. A mussel at a seep does not know it challenges assumptions about sunlight. A snailfish in a trench does not know it marks the edge of vertebrate survival. A microbe in hydrothermal fluid does not know it has astrobiological implications. These meanings are human overlays, useful and moving, but secondary. The deep sea is not trying to be profound. It becomes profound when humans finally pay attention. There is another way to enter this world, not by falling through the water, but by following a single grain of sand. It may begin on land, in a river cutting through mountain rock. Rain loosens soil. A stream gathers minerals, clay, fragments of shell, tiny pieces of forest, traces of towns and farms, and volcanic ash. The river carries them toward the coast, where fresh water meets salt, where estuaries breathe with tides. Some particles settle quickly, others move farther, caught by currents, lifted again by storms, carried across shelves and slopes,
until, eventually, the smallest grains make their way into deep water. By the time one of these grains reaches the abyss, it has become part of a history too long for the hand that might hold it. It settles into mud among microfossils, dust, organic fragments, and the waste of animals. A worm may swallow it. A current may lift it and place it elsewhere. A landslide may bury it beneath meters of sediment. A corer may bring it back to a ship 100,000 years later, and a scientist may split that core open under bright lights, reading the faint stripe where it came to rest. The bottom of the Pacific is made from such arrivals, not only the dramatic ones, not only whales and lava and chimneys. Most of what builds the seafloor is small beyond romance. Dust, ash, shells, clays, fecal pellets, skeletal fragments, microscopic plates of coccolithophores where they survive dissolution, silica from diatoms and radiolarians, the quiet remains of plankton that once floated in sunlight. The abyss is assembled from particles that have lost almost all resemblance to the lives they came from, and still, something recognizes them as food. A deposit feeder does not need a perfect meal. It can process sediment and take the little that remains. Its body is built around low yield. A surface animal might starve in such conditions, but the abyssal animal has no memory of banquets. It has inherited a world where abundance arrives rarely and incompletely. It eats the trace, the residue, the almost nothing. There is dignity in that kind of life. Not the dignity humans invent after hardship, but the dignity of a body precisely fitted to its reality. A sea cucumber, moving over the plain, is not aspiring toward another world. It is not waiting for the deep sea to become generous. It is doing what its lineage learned to do, turning thin sediment into continuity. In the mud around it, smaller animals live between grains. Nematodes, copepods, tiny worms, foraminifera, and other myofauna occupy the spaces too small for human attention, but large enough for entire lives. Their movements stir sediment in miniature. Their feeding shapes microbial communities. Their deaths feed others. If a camera cannot show them easily, the ecosystem does not become less real. The deep ocean is full of life below the threshold of spectacle. This is one reason the abyss can be misread from video alone. A camera gliding over mud may show only scattered large animals, while the sediment itself holds dense and varied communities at microscopic scales. The visible and invisible layers of the ecosystem overlap. A single square meter of seafloor can be visually quiet and biologically active. The eye, by itself, undercounts the world. The same is true in the water above the bottom. Transparent animals drift through blackness, gelatinous and fragile, often destroyed by nets before anyone understands their form. They may be predators, grazers, ambush hunters, drifting colonies. Some are so delicate that they can only be studied properly in place, using gentle collection or high-resolution imaging. The deep sea is not merely difficult because it is deep. It is difficult because many of its inhabitants fall apart when brought into the human world. Knowledge can be damaged by the act of collecting it. A jelly that holds its shape perfectly in the water may become a shapeless mass in a jar. A pressure-adapted animal may change when raised. A microbial community may shift when temperature and pressure are altered. A vent sample may lose chemical meaning once removed from the flow. Scientists work around these problems with pressure-retaining samplers, in situ sensors, careful imaging, and new methods. But the challenge remains. The deep ocean is not easily translated. To know it, we must learn to meet it where it is. This is why the best deep-sea exploration feels less like conquest than visitation. The machine descends, observes, samples lightly if it can, and leaves. The goal is not to dominate the landscape, but to understand enough to ask better questions. The ocean punishes any other attitude quickly. A cable tangles, a seal fails, a vehicle is lost, a storm ends the dive, a sample breaks, a current carries the instrument away. Humility is not decoration in the deep sea. It is practical. The Pacific has taken many machines. Some were experimental, built to push depth limits. Some were workhorses lost to pressure, terrain, or accident. The loss of a deep vehicle is more than financial. It can end a line of research, delay exploration for years, and remind everyone that the abyss remains stronger than the tools sent into it. The wreckage may rest on the sea floor, another human object entering deep time. A lost vehicle becomes part of the bottom it came to study. There is something sobering in that. The observer becomes artifact. The machine designed to reveal the abyss is absorbed by it. Metal corrodes, sediment gathers. Animals may shelter near it. Microbes colonize its surfaces. Eventually, it becomes less an interruption than a feature, though never a natural one. The ocean does not grant exceptions for purpose. Purpose belongs to us. Process belongs to the sea. Consider the shape of a deep-sea snailfish. It does not look like a creature built for conquest. Its body is soft, pale, almost tender. Its skin lacks the hard scales many fish carry. Its bones are reduced. Its muscles are not those of a fast surface predator. Its head is broad, its eyes small, its body almost translucent under lights. At hadal depths, this softness is not a defect. It helps the animal live without gas-filled spaces, without rigid structures that pressure would punish. The deepest known fish are snailfish, observed in trenches at depths beyond 8,000 meters. They move through a world where pressure changes the possibilities of vertebrate life. Research suggests there may be a depth boundary below which fish cannot maintain the chemistry needed for their cells to function, even with adaptations. Below that, the deepest animal life known becomes invertebrate. Amphipods, sea cucumbers, worms, isopods, microbes, and others. There is a strange tenderness in the idea that fish reach a limit, and then the world continues. Life does not stop where one branch cannot go. It changes caste. The hadal snailfish is remarkable not because it defeats the deep, but because it reveals a boundary. It shows how far one kind of body plan can be stretched. It is a messenger from the edge of fish possibility. Below it, the trench does not become empty. It becomes differently inhabited. Amphipods in the deepest trenches often look like small, pale crustaceans, but some can grow surprisingly large. In baited footage, they gather in numbers, their bodies curved and restless. They are scavengers, but that word can unfairly reduce them. Scavenging in the hadal zone is not a lesser lifestyle. It is one of the great solutions to an environment where food arrives unpredictably. The ability to find, consume, and process a sudden fall is vital. A carcass sinking to 10,000 meters becomes a signal spreading through water. Chemical traces move outward. Animals detect them. They converge. For a brief time, the trench floor becomes dense with activity. Then the feast is gone, broken down, incorporated, dispersed. The crowd thins, the mud returns to quiet. The event may be rare for any one patch of seafloor, but across the immense Pacific, such events are part of the rhythm. Death falls constantly in small amounts, occasionally in large ones. The deep sea waits not in idleness, but in readiness. Readiness is a form of adaptation. Some animals store energy, some slow their metabolism, some produce many larvae, some live long enough to outlast scarcity. Some rely on symbionts, some feed opportunistically, some burrow, some drift. Each strategy is a way of answering the same question: how do you remain alive when the world gives little and gives irregularly? On the abyssal plane, the answer may be patience. At vents, it may be speed and tolerance. At seeps, it may be partnership and longevity. In trenches, it may be pressure adaptation and opportunism. On seamounts, it may be catching currents. At whale falls, it may be succession. No single answer defines the bottom. The Pacific bottom is a library of solutions to darkness. In the middle of that darkness, bioluminescence appears like punctuation. Near the sea floor, some animals produce light, though not in the same overwhelming density seen in parts of the midwater. A flash may startle a predator, attract prey, communicate with a mate, or confuse an attacker. Some brittle stars can glow. Some sea cucumbers release luminous material when disturbed. Some fishes carry photophores or use light in subtle ways. The colors are often blue or green because those wavelengths travel best through seawater. Red light disappears quickly in the ocean, making red animals appear black at depth under natural conditions. Some deep-sea creatures are red not to be seen, but to vanish. Color becomes a strategy in a world with little color. When a submersible's white light falls on them, the illusion breaks. A red shrimp becomes red because humans have brought the missing wavelengths. A fish appears brown or purple. A worm's plume glows crimson. The artificial light creates a version of the animal its neighbors may never see. Documentary footage, then, is not neutral. It beautifies, reveals, disturbs, alters. It shows deep animals under conditions that are not their own. Yet, without it, most people would never see them at all. The image is both gift and compromise. The deep ocean lives inside compromises. To protect it, humans must study it. To study it, humans must enter it. To enter it, we disturb it. The task is to make the disturbance small, thoughtful, justified, and honest. There is no pure observation, but there can be careful observation. Carefulness in the deep sea can look like moving a manipulator arm millimeter by millimeter so a sample is collected without crushing nearby life. It can look like choosing not to collect a rare animal because the video is enough. It can look like designing experiments that leave minimal marks. It can look like sharing data openly so fewer duplicate disturbances are needed. It can look like setting aside protected areas before exploitation begins. It can also look like telling the story well enough that the bottom becomes imaginable. Imagination is not science, but it can defend what science reveals. A person may never see an abyssal sponge in person, but if they can imagine it anchored to a nodule in black water, filtering a cold current for decades, perhaps it becomes less disposable. If they can imagine a trench seep community thriving at 9,000 meters, perhaps the phrase deep-sea mining loses its abstraction. If they can imagine a whale fall turning death into habitat, perhaps the ocean floor becomes less like emptiness and more like a living country. The bottom needs witnesses, even indirect ones. This does not mean every story should be sentimental. The deep sea is not asking to be humanized. It is not lonely. It is not brave. It does not need our adjectives to exist. But human care often begins when the mind can linger. A good image, a precise fact, a quiet scene. These can give attention somewhere to rest. A tube worm at a vent is not a symbol first. It is a tube worm. Let it be that, and it becomes more powerful, not less. The Pacific's hydrothermal vents vary widely. Some are dominated by giant tube worms, others by shrimp, mussels, snails, crabs, or microbial mats. Chemistry differs. Depth differs. Geological setting differs. A vent on the East Pacific Rise is not identical to a vent in a Western Pacific back arc basin. Some fluids are rich in sulfide, some in hydrogen. Some systems are influenced by serpentinization, where seawater reacts with mantle rocks and produces hydrogen and methane. Each chemistry invites different microbial metabolisms and animal partnerships. The public image of the black smoker is only one chapter. There are white smokers, diffuse flows, warm cracks, shimmering fluids, low-temperature vents, acidic conditions, metal-rich plumes. Some venting is dramatic, some almost invisible. The sea floor may reveal it through bacterial mats, unusual animals, chemical sensors, or temperature anomalies. A vent field can be discovered by following clues in the water column. A plume of particles, methane, helium isotopes, temperature, turbidity. Exploration becomes detective work. A ship tows sensors through deep water. Scientists watch readings for anomalies. Something in the water is slightly warmer, slightly cloudier, chemically unusual. The signal suggests a source below. The search narrows. An autonomous vehicle maps. An ROV dives. The bottom appears. At first, rock, then shimmering water, then a chimney, then life. The discovery of a vent field is not just finding a place, it is finding an energy system. The same detective work applies to seeps, methane anomalies, carbonate outcrops, bacterial mats, chemosynthetic clams, pockmarks on the sea floor, acoustic signals from gas. A seep may be hidden under sediment until the right instrument sees its trace. The ocean floor is full of subtle exhalations. At cold seeps, the pace may feel slower, but the ecology can be equally rich. Long-lived tube worms may form thickets. Mussels and clams house symbiotic bacteria. Microbial mats oxidize methane or sulfide. Carbonates create hard substrate. The seep becomes a stable island in soft sediment, supporting animals not found in surrounding mud. Seeps also connect to the global methane cycle. Methane is a potent greenhouse gas if it reaches the atmosphere, but much methane released in marine sediments is consumed by microbes before it enters the water column or air. The deep sea floor is therefore not only habitat, but filter. Microbial communities mediate the movement of carbon from sediment to ocean. Again, the invisible becomes planetary. A microbe at a seep may never be filmed, but its metabolism matters. Hydrothermal vents and cold seeps changed the way scientists think about the limits of life. They also changed the emotional map of the deep sea. Before their discovery, the abyss could be imagined as a dark desert fed from above. Afterward, the bottom became more complex, still often food poor, but punctuated by places where the earth itself provides energy. The deep sea was no longer only a receiver of sunlight's leftovers. It was also a generator of life through chemistry.
This does not mean sunlight is irrelevant at vents and seeps. Oxygen in deep water is produced largely by photosynthesis at the surface, and many animals in chemosynthetic communities still depend on oxygenated seawater. Some food webs are mixed, drawing from both chemosynthetic and photosynthetic sources. The deep ocean resists clean separations. Sunlight and earth chemistry meet there in indirect ways. A tube worm's bacteria may use sulfide,
But the worm's blood also carries oxygen that came from the surface ocean. Even life without sunlight may breathe the sun's byproduct. The world is tangled. The phrase, life without sunlight, is powerful, but the truth is subtler. At vents, life can be based on chemical energy rather than photosynthetic organic matter. Yet the broader ocean system still connects to surface processes. This subtlety does not reduce wonder. It deepens it. It shows that independence is often partial, that ecosystems are layered, that even the most alien communities remain earthly. The bottom of the Pacific is not a place where one grand rule replaces another. It is where many rules overlap. Abyssal life depends on falling food. Vent life depends on chemical energy. Seep life depends on fluid flow and microbial transformation. Hadal life depends on pressure adaptation, food concentration, and sometimes chemical sources. Seamount life depends on current and hard substrate. Microbial life depends on gradients too small for eyes. All of these are true at once. The challenge for storytelling is to keep them from collapsing into simplification. The deep sea is not barren except for vents. It is not teeming everywhere. It is not untouched. It is not already ruined. It is not alien in a way that separates it from us. It is not familiar in a way that makes it easy. It is uneven, specific, dynamic, and incompletely known. A truthful voiceover must allow unevenness. Some scenes should be quiet because the bottom is quiet. Some should be astonishing because it is astonishing. Some should be technical because reality has mechanisms. Some should be emotional because humans are listening. On a seamount, the current strengthens. Water that drifted slowly over the plain is forced upward and around the slope. Particles concentrate. Animals take advantage. Corals grow where larvae found rock and flow. Sponges lift themselves into the current. Fish hover nearby. Predators patrol. The seamount becomes a vertical interruption in the abyss, a place where geography creates opportunity. Deep-sea corals do not need sunlight because they are not dependent on photosynthetic algae in the way shallow tropical corals are. They catch food from the water. Some build branching structures that create habitat for other organisms. Their growth can be slow. Their skeletons can record environmental conditions. Their communities may be vulnerable to bottom trawling, mining, and climate-related changes. A coral garden in darkness can be as intricate as any shallow reef, though its colors appear only under artificial light. Pink, white, orange, red, gold. In natural darkness, much of this color has little visual meaning, yet the pigments remain, revealed by visiting machines like secrets the animals did not intend to keep. The idea of a garden without sunlight feels contradictory, but the deep sea is full of such contradictions. Forests of animals where no plant grows, snow with no clouds, smoke with no fire, rivers of dense brine in some deep basins, lakes beneath the sea in other oceans. At the bottom of the Pacific, language borrowed from the surface stretches and sometimes breaks. Maybe that is why narration often becomes poetic around the deep. Not because poetry is decoration, but because literal words alone can seem too narrow. The science is precise, the experience is uncanny. Both are needed. A deep-sea sponge may have a skeleton of silica so intricate it looks designed by mathematics. Some glass sponges form lattices that have inspired engineers. They filter huge volumes of water, host microbial communities, provide habitat, and grow in places where current brings food. They can be ancient, delicate, and structurally extraordinary. In the beam of an ROV, A glass sponge can look like architecture built by patience.
Nearby, a brittle star wraps itself around a branch, arms extended to catch particles. A shrimp moves along a surface. A small fish shelters in the structure. The sponge is not just an individual, it is a place. Much of the deep ocean is built from living places: coral branches, sponge stalks, tube worm bushes, mussel beds, clam fields, whale bones, nodule surfaces, bacterial mats. Each creates conditions for others. Habitat is not always geological. Sometimes it is biological. This matters because removing one organism can remove many relationships. A trawl that breaks coral does not only kill coral, it removes shelter, feeding surfaces, egg-laying sites, current structures, microbial associations, and historical continuity. A mining machine that removes nodules does not only take minerals, it removes hard substrate in a soft sediment world. A sediment plume does not only cloud water, it may clog feeding structures, bury small animals, alter chemical exchange. Impact is relational. The deep sea's relationships are often poorly mapped. This combination, complex relationships and limited knowledge, should slow human confidence. Yet economic pressure often moves faster than knowledge. The Pacific bottom is becoming a test of whether humanity can act cautiously in a place that does not force caution through immediate, visible suffering. The abyss will not burn like a forest on television. A disturbed nodule field will not send smoke over cities. A lost worm species will not trend because almost no one knew its name. The deep sea's danger is that damage can be quiet. But quiet damage is still damage. A sediment plume spreading near the bottom may look like a cloud. It can travel depending on particle size, currents, topography, and the activity creating it. It may resettle over animals adapted to clear, low sediment conditions. It may dilute, spread, or concentrate. Models and experiments continue to study this, but uncertainty remains. The deep ocean is three-dimensional, dynamic, and difficult to monitor at scale. Noise from industrial activity could also matter. Many marine animals use sound or vibration. The deep soundscape already carries natural and human-made signals. Adding chronic noise to poorly understood habitats raises questions science has not fully answered. Light from machines, too, may affect animals evolved in darkness. The act of working in the deep introduces sensory disturbances that shallow water creatures might avoid, but deep animals may be less prepared to encounter. The bottom's remoteness does not make industrial activity simple. It makes oversight difficult. International waters add another layer. Much of the Pacific abyss lies beyond national jurisdiction, in areas governed by international frameworks. Decisions about mining, conservation, and research become global questions. The deep seabed has been described in legal language as part of the common heritage of humankind. But heritage is a demanding word. It implies responsibility, not merely shared access. If the abyss belongs to humanity in some legal sense, then humanity owes the abyss more than appetite. It owes understanding, restraint, memory. The deep sea has already given humans much without being mined. Climate regulation, carbon storage, biodiversity, scientific insight, new enzymes and molecules, perspective on life's limits, analogs for other worlds, beauty that unsettles arrogance. These gifts are not always counted because they are not easily priced. The bottom of the Pacific reminds us that value can exist outside immediate use. A vent worm may never benefit an economy. A trench amphipod may never become a medicine.
A microbe may never be patented. A nodule field may be worth more left intact than humans know how to calculate. This does not mean practical benefits are irrelevant. Deep-sea research has led to technological innovation and biological discoveries. Extremophile enzymes can matter. Chemical compounds from marine organisms may have medical potential. Understanding carbon cycling can improve climate models. Mapping hazards can protect coastal communities. The deep is useful, but usefulness is a poor ceiling for wonder. Life does not need to be useful to be worth knowing. In the middle of the Pacific, far from land, the surface can be so calm that the horizon disappears into haze. A research vessel may drift above 4,000 or 5,000 meters of water, its engines holding position. From the deck, nothing about the surface suggests the landscape below. The ship could be above a plain, a seamount, a fracture zone, a field of nodules, a dead whale, an old lava flow, a community of animals no one has seen. The ocean keeps its secrets vertically. A crew member may look over the rail at blue water and think of home, weather, work, the next watch. Beneath the hull, the water column drops farther than the height of most mountains. The ship's instruments know this. The human body does not feel it. We stand above the abyss without vertigo because water hides the fall. If the water became transparent all at once, the sight might be unbearable. A person would look down through kilometers of blue into black, past migrating layers of animals, past drifting snow, past the last light, to a floor almost impossibly far below. The Pacific would become not a surface, but a depth, and perhaps humans would speak of it differently. But the water is not transparent, so imagination must do the descent. The descent is not only physical, it is cultural. For centuries, the deep ocean occupied human thought as danger, myth, unknown, grave, monster country. Sailors knew its surface moods intimately, but not its depths. The sounding line gave numbers. Dredges brought up organisms from depths once assumed lifeless, challenging 19th century ideas. Expeditions expanded knowledge. Submersibles and cameras transformed mystery into imagery. Now the deep sea sits at the intersection of science, industry, climate, conservation, and awe. Our relationship with it is still young. The bottom has existed for eons. Human knowledge of it is a recent flicker. This imbalance should shape the tone of any story. We are newcomers speaking about an ancient dark. We can speak beautifully, carefully, scientifically, but we should not sound as if we have mastered it. Mastery is the wrong mood. Attention is better. At night, on a research vessel, the control room glows while most of the ship sleeps. The ROV is on the bottom. Outside the ship, waves slap the hull. Inside, screens show mud, rock, animals, instrument readouts. Someone notes the time. Someone labels a sample. Someone whispers because the scene on screen feels like a sleeping animal's room. A crab moves through the light. A scientist who has spent years studying these systems may still lean forward. Expertise does not remove wonder. It refines it. The expert sees more: the species, the substrate, the behavior, the implication of chemistry, the unusual depth, the possible new record, the sign of disturbance, the clue hidden in sediment color. Where a casual viewer sees a white worm, the expert sees a relationship between sulfide, oxygen, symbiosis, and tectonics. Wonder becomes more detailed. That may be the best kind. The bottom of the Pacific rewards detailed wonder. It does not need exaggerated monsters or invented drama. A true description of pressure is enough. A true description of chemosynthesis is enough. A true description of a sea cucumber processing mud for food is enough, if the attention is honest. There is also an emotional discipline in not making every image a metaphor. Sometimes a shrimp is just a shrimp. Sometimes mud is mud. The narration should breathe enough to allow simple observation. The deep sea is already carrying more meaning than any voice can hold. The storyteller does not need to wring profundity from every sentence. A vent crab climbs over a mussel bed. A plume bends in the current. A white fish rests on sediment. A particle falls past the lens. Let it happen. Then, when the larger thought comes, it will feel earned. One of the larger thoughts is this: life at the bottom of the Pacific is not separate from death. It is built from death, as all ecosystems are, but the deep makes the connection visible. The marine snow is mostly dead or dying matter. Carcasses become feasts. Whale bones become chemical habitats. Woodfalls become islands. Sediment is layered with remains. Even vent communities depend on microbial transformations of chemicals that are not alive, but become life. The deep sea is a place where the boundary between ending and beginning is continuously crossed. A whale dies near the surface. Its body sinks. Scavengers remove flesh. Bone-eating worms bore into the skeleton. Bacteria break down lipids. Sulfide supports chemosynthetic microbes. Other animals graze, shelter, reproduce. Years pass. The bones thin. Sediment covers what remains. The whale is no longer a whale, but its matter persists in the community. This is not a metaphor for resurrection. It is ecology. Ecology is often more profound than metaphor because it does not require comfort. The whale is gone. The whale continues. Both are true. At hydrothermal vents, the relationship between destruction and creation is equally stark. The same volcanic forces that open habitat can bury it. Lava can wipe out communities. New venting can create new ones. Species adapted to vents must live with catastrophe as part of the landscape. Disturbance is not always outside the system. Sometimes it is the system. But natural disturbance has patterns, histories, and evolutionary context. Human disturbance may differ in intensity, scale, frequency, and novelty. The deep sea's familiarity with eruption does not mean it is prepared for mining. A trench's experience of landslides does not mean it is prepared for persistent pollution. A whale fall's pulse of organic matter does not mean it is prepared for plastic. Analogies can mislead. The bottom teaches specificity again. What kind of disturbance? How often? How large? In what habitat? For which species? Under what recovery conditions? These are the questions that matter. The Pacific also holds zones where oxygen minimum layers occur above parts of the seafloor, influencing life along margins and slopes. Off some continental margins, low oxygen waters shape communities, favoring species adapted to hypoxia. Where oxygen is scarce, animals may be smaller, slower, or specially adapted. Microbial processes change. Nitrogen cycling can be intense. The bottom is influenced by the chemistry of the water masses bathing it. Oxygen is invisible, but life follows it. A camera might show fewer large animals in one area, more in another, and the reason may not be obvious visually. It may lie in dissolved oxygen, food flux, sediment grain size, current, pH, or history. The deep sea's mysteries are often not hidden behind spectacle, but behind variables. This is why deep-sea ecology relies on measurement. Temperature, salinity, oxygen, pressure, currents, methane, sulfide, pH, particulate organic carbon, sediment chemistry, isotopes, DNA, bathymetry. Without these, the image is only image. Yet the image matters because it restores presence. Data can tell us a community exists. Footage lets us encounter it. A balance is needed. Enough science to be truthful, enough atmosphere to be felt. The bottom of the Pacific is not a textbook, but it deserves accuracy. The pressure increases about 1 atmosphere every 10 meters. Sunlight does not penetrate the abyss. The deepest known point is in the Mariana Trench. Chemosynthesis uses chemical energy to fix carbon. Abyssal plains are among Earth's largest habitats. Hydrothermal vents were discovered with rich communities in 1977. Hadal trenches host active ecosystems. These facts are anchors. Around them, the story can move like water. Facts without atmosphere become lecture. Atmosphere without facts becomes fog. The deep ocean needs both clarity and darkness. Somewhere along the Pacific margin, a cold seep releases methane from sediment. It may have been doing so long before anyone mapped it. The seep community grows around it slowly. Clams settle, bacteria spread, carbonate forms, worms extend, fish visit. The seep becomes a neighborhood with chemical streets. A scientist might describe it in terms of anaerobic oxidation of methane, sulfate reduction, carbon cycling, symbiotic bivalves. The description is correct, but the camera shows something else too. A pale, living patch in black mud, a quiet exception to the surrounding plain, an opening where the earth leaks nourishment. Both descriptions are needed. One tells how it works, the other tells how it feels to find it. At a vent, the feeling is more immediate. The water shimmers, the chimney towers, animals crowd. The first sight can be almost unbelievable because the scene contradicts expectations so completely. At depth, in darkness, under pressure, with toxic chemicals and no sunlight, there is abundance. The mind tries to correct the image, to make it less impossible. Then the science explains it, and the explanation makes it more astonishing, not less. Chemosynthesis is one of those concepts that changes the emotional shape of biology. It means life can build itself from energy sources other than light. It means the sun is not the only doorway. It means Earth's interior and ocean chemistry can support food webs. It broadens the idea of habitability, but it also reveals dependence on conditions that can be narrow. A vent community cannot simply move anywhere in the abyss. It needs the flow. It needs the chemistry. It needs the gradient. Its independence from sunlight is not independence from place. All life is provincial in some way. Humans forget this because technology makes us mobile. But even humans remain tied to pressure, oxygen, temperature, food, water, microbes, climate. A submersible lets us visit the bottom, but only by carrying a tiny artificial surface world with us. Air, warmth, pressure protection, light, power. We do not become deep-sea animals when we descend. We remain surface animals inside a shell. The animals outside are the true residents. Their bodies are passports we do not possess. A Dumbo octopus hovering over abyssal sediment does not need a titanium sphere. It does not need a support ship. It does not need a weather window. It belongs directly to the pressure. This simple fact can feel more impressive than any machine. Human engineering is extraordinary because it survives briefly where the octopus lives ordinarily. The deepest animals are not visitors to extremes. They are locals. That word, locals, changes the emotional frame. The trench is not an extreme environment to a hadal amphipod in the way it is to us. It is home. The vent is not a hostile anomaly to a vent mussel. It is habitat. The abyssal plain is not empty to a deposit feeder. It is the ground. Calling the deep sea extreme is accurate from a human perspective, but incomplete from theirs. Every habitat is extreme to the unadapted. A desert is extreme to a fish. Air is extreme to a deep-sea worm. The surface ocean, with its light, turbulence, predators, and ultraviolet radiation, might be lethal or irrelevant to many bottom species. We live in each other's impossibilities. This thought brings the deep closer. It does not make it familiar, but it makes our perspective less absolute. The bottom of the Pacific is not a failed surface. It is a successful bottom. Life there is not surviving despite its world. It is living because of its world. At a vent, remove the darkness and pressure, remove the chemistry, remove the gradients, and the community changes or dies. At a seep, stop the methane and sulfide, and the foundation shifts. On the abyssal plain, increase sedimentation suddenly or remove nodules, and the habitat is altered. These animals are not waiting to be rescued into conditions we prefer. Conservation, then, is not about making the deep sea more like our world. It is about allowing it to remain itself. This can be difficult for humans because we often protect what we can easily love. The deep asks us to protect difference. Not a landscape we could walk through, not animals that meet our gaze in familiar ways, not ecosystems that fit old metaphors, but a realm where life is slow, dark, and chemically strange. It is an advanced form of care. There is also joy in it. The joy of discovering that Earth is more inventive than expected. The joy of seeing a creature so strange that laughter and awe arrive together. The joy of realizing that a place dismissed as barren is full of hidden process. The joy of knowing that even under unimaginable pressure, life has not disappeared. This joy should not become triumphalism. The deep sea is not proof that life can survive anything. It is proof that life can adapt to specific things over deep time. It is proof of creativity within limits. It is proof that human assumptions are often too small. That is enough. More than enough. On a Pacific abyssal plain, a small anemone may anchor to a rock or nodule, opening delicate tentacles into the current. Its body is simple in outline, but its survival depends on the presence of substrate, food particles, water movement, reproductive timing, and the absence of smothering disturbance. It may live in a place where the next hard surface is far away. Its existence is a tiny occupation of opportunity. A shrimp at a vent may graze bacteria, avoiding lethal heat. A clam at a seep may bury itself just enough to access sulfide, while extending to oxygenated water. A polychaete worm may build a tube. A brittle star may climb a sponge to feed higher in the current. A fish may wait beside a structure because prey gathers there. Behavior makes habitat visible. When animals choose positions, they reveal gradients humans might miss. Where they cluster, something is happening. Where they avoid, something else is happening. Biology can be a sensor. A field of clams may indicate seepage. A microbial mat may show chemical flux. A change in species may mark oxygen or substrate differences. Life reads the bottom before instruments do. Scientists learn to read life reading the bottom. This layered perception is beautiful. The animal responds to chemistry. The scientist responds to the animal. The viewer responds to the image. Meaning travels upward like a signal. The Pacific bottom also contains absence as data. A baited camera may show no fish below certain depths, supporting ideas about pressure limits. A nodule removal track may show slow recovery. A vent field may lack species common elsewhere, revealing biogeographic boundaries. A sediment core may show low biomass, indicating energy limitation. What is not present can matter as much as what appears.
Absence, carefully interpreted, becomes information. But absence can also be misread. Not seeing an animal does not mean it is not there. One dive in one season under one condition is not a complete survey. The deep sea demands caution in both directions. Do not exaggerate from a glimpse, but do not dismiss the glimpse either. A single observation can open a field. The first discovery of rich vent communities did. The first images of hadal snailfish did. The documentation of deep chemosynthetic communities in Northwest Pacific trenches did. Each began as observation and became revision. Science is often portrayed as certainty replacing mystery. In the deep sea, science often makes mystery more precise. It tells us exactly where the unknown begins. For example, discovering dense chemosynthetic communities at depths over 9,000 meters answers one question: can such communities exist so deep? And opens many others. How widespread are they? How old are they? How do larvae disperse among trenches? What chemicals sustain them? How do their symbionts function under pressure? Are the species new? How vulnerable are they to disturbance? What do they imply about carbon cycling in trenches? A discovery is a doorway, not a final room. The bottom of the Pacific is full of doorways. Some are literal cracks in the seafloor. Some are biological partnerships. Some are technological thresholds. Some are questions that appear only after a machine survives long enough to look. A lander descending to full ocean depth experiences the water column as a long fall through increasing pressure and darkness. It may carry weights that will be released for ascent, floats engineered to survive compression, cameras, lights, bait, sensors, sample containers. It has no pilot. It falls by gravity, works alone, and returns when commanded acoustically. For hours, it is a small, unattended object in the largest habitat on Earth. When it reaches the bottom, it may stir a small cloud of sediment. Then it waits. Its lights may turn on at intervals. The bait releases scent. Animals arrive. The camera records. Instruments log pressure, temperature, oxygen. After the mission, a signal from the ship tells it to drop weights. It rises slowly through darkness, carrying images and samples from a place no human hand could touch directly. The recovery can be tense. The ocean is large. Weather changes. The lander must surface where it can be found. A flag, strobe, radio beacon, or satellite signal helps. The crew spots it, retrieves it, opens it. Inside are traces of the hadal world: water, sediment, animals, data. The bottom has come back, temporarily, in fragments. There is a strange intimacy in opening a trap from the deep. Amphipods that lived under crushing pressure are suddenly under ship lights. Mud from the trench sits in a container on deck. The distance collapses. Scientists move quickly to preserve, measure, photograph, freeze, or maintain pressure if possible. The sample begins changing the moment it leaves its world. Every deep-sea sample is urgent because it is displaced. The ethics of sampling are complex. Without specimens, species cannot always be described, anatomy cannot be studied, genetics cannot be verified, physiology cannot be understood. But sampling removes life. The answer is not never collect.
It is collect with purpose, restraint, and respect. Respect in science is not sentimentality. It is rigor joined to care. A poorly labeled sample dishonors the animal because it wastes the taking. A careless disturbance dishonors the habitat because it gains little knowledge. A careful collection, documented and shared, can give the animal scientific presence beyond its death. This is uncomfortable, but much knowledge of life has always carried such discomfort. The deep ocean does not simplify the relationship between wonder and harm. It forces honesty about it. In the control room, when a rare animal appears, scientists may debate whether to collect it. If it is likely new, a specimen matters. If only one is visible, collection may feel heavy. If the animal is fragile, it may not survive sampling. If the habitat is vulnerable, the manipulator may cause damage. Decisions happen in real time, under excitement and uncertainty. The public often sees only the beautiful footage later. The choice behind the footage is part of the story. To study the bottom of the Pacific is to make choices in darkness. This phrase applies beyond science. Humanity is making choices in darkness about climate, extraction, pollution, and protection. The deep ocean is not fully known, but decisions cannot wait for perfect knowledge. The ethical challenge is to let uncertainty increase caution rather than license. The abyss has been patient with our ignorance. It may not be resilient to our confidence. Some researchers argue for precautionary pauses before large-scale deep-sea mining. Others work to establish environmental baselines, impact models, monitoring tools, and protected networks. Industry groups develop technologies. Nations debate rules. Conservationists call attention to biodiversity. The conversation is technical, political, and emotional. Beneath it lies a simple fact. The bottom itself cannot speak in human forums. Its advocates must translate mud, worms, nodules, microbes, and darkness into language that decision-makers can hear. This translation is difficult because the bottom's value is not obvious to systems built around immediate extraction. A nodule has market value once removed. A living nodule field has ecological value that is harder to price. A species unknown to science has no market category. A microbial process may matter globally, but invisibly. A slow recovery time is a cost placed on the future, where accounting often grows weak. The deep sea exposes the limits of economic imagination, not because economics is useless, but because some values resist its simplest forms. A living abyss is not just a stock of minerals plus unknown organisms. It is a functioning part of Earth. The more one learns, the less adequate the word resource becomes. Resources are for use. Relationships are for responsibility. The bottom of the Pacific is both material and relationship. It contains metals, carbon, microbes, animals, minerals, sediments, water. But it also contains dependencies, histories, cycles, and possibilities. To see only materials is to see as a machine might see. To see relationships is to begin seeing ecologically. The deep sea asks humans to become better witnesses before becoming users. In some places, protection already exists or is being proposed. Marine protected areas, vulnerable marine ecosystem closures, environmental management plans, areas of particular environmental interest. These tools are imperfect, but they represent an attempt to give spatial form to care. The difficulty is that deep-sea ecosystems can be poorly mapped, and connectivity may extend beyond boundaries. Protecting one patch may not protect larval sources. Avoiding one feature may not protect sediment plume pathways. Conservation in the deep requires humility, plus science, plus governance over timescales longer than election cycles. That is a hard combination. But the ocean has always required hard combinations. The Pacific bottom, for all its darkness, is not hopeless. It is still vast. Much of it remains functioning. Many habitats are undisturbed by direct human contact, though not untouched by global change. There is still time to study before acting in many areas. There is still time to design protections, improve mapping, reduce pollution, regulate noise, weigh mining decisions carefully, and expand public understanding. The deep sea is not asking for despair. Despair is another way of turning away. Attention is better. A slow camera over a nodule field, a careful map of a seamount, a treaty debate informed by ecology, a school child seeing a vent worm and understanding that sunlight is not the only foundation, a policymaker realizing that mud can be habitat, a scientist naming a species before it disappears, a storyteller refusing to call the abyss empty. These are small acts, perhaps, but the bottom itself is built from small acts accumulating, particle by particle, layer by layer, observation by observation, care by care. The deep Pacific's life also carries clues about evolution under constraint. Pressure-adapted proteins, membrane structures, osmolytes, metabolic pathways, reproductive strategies, sensory adaptations. Each tells a story of selection in conditions far removed from the surface. Studying these organisms helps scientists understand not only the deep sea, but the flexibility of life itself. For example, the molecules that help some animals stabilize proteins under pressure are not magical shields. They are chemical adjustments with trade-offs. A compound useful at high pressure may be costly in other ways. Adaptation is rarely free. It is a set of compromises written into bodies. Deep-sea fish often have low metabolic rates, watery tissues, reduced skeletal structures, and adaptations to darkness. Some have large mouths or expandable stomachs to handle rare meals. Others rely on slow cruising or ambush. Many deep-sea animals produce fewer, larger eggs or have larvae that disperse in the water column. Life histories vary, but many are tuned to low energy. The deep ocean is not simply a place where animals become bizarre for no reason. Their forms are explanations. A huge mouth says meals are rare and must be taken when available. A transparent body says visibility matters even in dim light. A reduced eye says vision has changed in importance. A soft body says pressure and energy economy matter. A symbiotic organ says microbes are feeding the animal. A long fin ray says waiting in current is useful. A slow growth rate says energy is limited and time is different. Evolution has written environmental conditions into anatomy. The Pacific bottom is therefore readable through bodies. A tube worm's missing gut, a snailfish's soft tissues, a sponge's lattice, a sea cucumber's feeding tentacles, an amphipod's scavenging mouthparts, a clam's symbiotic gills. These are not curiosities. They are sentences in the language of adaptation. When humans call deep-sea animals strange, we often mean they are poorly translated into our expectations. In their own language, they are clear. A black smoker chimney also has anatomy, in a geological sense. Its walls are layered with minerals. Channels carry hot fluid. Chimney shapes reflect flow, chemistry, collapse, and growth. Microbes may live within porous structures, occupying temperature and chemical gradients. The chimney is both rock and habitat, both plumbing and architecture. A vent field can be mapped not only by animals, but by mineral structures and fluid chemistry. Temperatures can reach extremes, but animals live in mixing zones where conditions are survivable. The visual drama of black fluid sometimes hides the finer scale organization around it. Life is not in the hottest plume itself, but along edges where chemistry and temperature create possibility. Edges again. The bottom is an edge-making world. On whale bones, bone-eating worms of the genus Ocedax can colonize, using symbiotic bacteria to help extract nutrients from bone. They have no mouth or gut as adults, instead growing root-like structures into the bone. Their discovery was another reminder that the deep sea holds specialized forms of life around temporary habitats. A whale skeleton becomes not only food, but a niche that some animals are built to exploit. Think of the improbability from a human perspective. A worm whose life depends on bones falling into darkness. From the worm's perspective, it is not improbable. It is ancestry. Evolution does not need common events everywhere. It needs recurring opportunities over enough time. Whale falls may be rare at a given point, but across ocean basins and evolutionary timescales, they are real habitats. Wood falls, kelp falls, jelly falls, fish carcasses, all create pulses of energy that specialists can exploit. The deep sea's patchiness is not disorder, it is the pattern. Abyssal animals may use chemical cues to locate food falls. Larvae may drift until they encounter settlement cues. Scavengers may move long distances. Microbes bloom quickly when energy appears. The community changes through succession, one group preparing conditions for another. Ecology unfolds not only across space, but through stages. A whale fall's first stage is mobile scavengers, then enrichment opportunists, then sulfophilic communities, where bone lipids fuel sulfide production. Eventually, reef-like remains may persist. The stages overlap and vary, but the principle is powerful. A single body becomes a multi-year ecological process.
The bottom of the Pacific is therefore not just a place of resident communities. It is a place of events that become habitats. A dead whale is an event. A volcanic eruption is an event. A seep opening is an event. A landslide is an event. A mining disturbance would be an event. The difference lies in origin, frequency, scale, and recovery. The deep sea has always had events. The question is, what happens when human events enter the pattern faster than deep life can absorb? At the deepest trenches, the shape of the seafloor can trap organic matter, making hadal zones sometimes richer in food than nearby abyssal plains. Steep walls funnel material downward. Earthquakes and slope failures can deliver pulses. This may help explain why trenches, despite extreme pressure, support active communities. The hadal zone is not merely a deeper desert, it can be a collector. This collection has consequences for carbon cycling. Organic matter transported into trenches may be buried or processed. Microbial activity can be significant. Trenches occupy a small fraction of the seafloor area, but may play roles disproportionate to their size in certain biogeochemical processes. Scientists continue to investigate how important these roles are globally. Again, the bottom complicates scale. A small area can matter if the process is intense. A seep patch can support dense life. A vent field can transform local chemistry. A trench can concentrate carbon. A nodule can anchor a sponge. A microbe can feed a worm. The deep ocean works through disproportions. One of the most cinematic journeys in the Pacific would begin at a coral reef and end in a trench. Not because the reef and trench are opposites, but because they are connected by the same ocean. Start in sunlight, among reef fish, coral polyps, algae, warm currents. Move offshore to blue water, where tuna hunt and plankton drift. Descend through the twilight migration, where lanternfish rise at night and bioluminescence writes brief signals.
Continue into the midnight zone, where pressure increases and bodies become stranger. Reach the abyssal plain, where mud records the fall from above. Follow the plain to a seamount, where corals grow in darkness. Move to a vent, where chemistry feeds dense life. Follow the plate toward a trench, where the seafloor bends downward into hadal depth. End at the deepest mud, where amphipods find a carcass in the dark. This is not a fantasy route. It is a conceptual cross-section of the Pacific's living architecture. The ocean is not one habitat. It is a stacked and folded multitude. Humans often flatten it with the word ocean, as if naming the whole makes it simpler. But the Pacific contains more environmental variety than many continents. Tropical surfaces, polar connections, oxygen minimum zones, productive upwellings, oligotrophic gyres, abyssal plains, trenches, ridges, vents, seeps, seamounts, island arcs, continental margins. Each has life shaped by conditions. The bottom is only one part of this, but it receives from all the others. That is why life at the bottom cannot be understood by looking only down. One must look up to surface productivity and climate, sideways to currents and connectivity, beneath to geology and fluids, backward to evolution and sediment history, forward to human choices. The bottom sits at the convergence of directions. A particle falls from above, a fluid rises from below, a current moves across, a plate moves sideways and downward, a larva drifts, a machine descends, a decision made far away arrives eventually. This is the geometry of the deep Pacific. The emotional power of the deep sea also comes from its indifference. Not cruelty, indifference. The bottom existed before human stories and will not rearrange itself to fit them. A submersible's light does not make it more alive. A name does not make a species begin. A law does not make a habitat valuable. These things matter to us, and through us they may matter to the future of the bottom, but the seafloor itself has no need of our recognition. And yet, recognition changes our behavior, so the story matters. There is a paradox. The deep sea does not need to be seen, but it may need to be seen by us in order to be spared from our ignorance. A creature in the abyss may live perfectly without human attention, but if human industry approaches, attention becomes a kind of defense. Cameras, maps, species descriptions, ecological studies, public imagination, all become ways of saying, something is here. Something was already here. Something continues here. This may be the most important sentence in deep-sea conservation. Not there might be resources, not there might be strange life, but something is here. A field of nodules is not waiting empty. A trench is not an unused space. A vent is not a curiosity detached from consequence. A seep is not a stain. The bottom is occupied. The occupants are not human, but occupation does not require humanity. At times, deep-sea imagery can create the impression that the bottom is always being watched. In reality, observation is vanishingly rare. The camera footage that circulates publicly may come from a tiny number of dives. The seafloor outside those paths remains unseen. Even where mapping exists, biological observation may be sparse. The Pacific is so large that our explored patches are like pinholes in a theater curtain. Behind the curtain, the play continues. This ratio between seen and unseen should make us cautious about definitive statements. We know enough to be amazed. we do not know enough to be complacent. A good long-form story about the bottom should leave the audience with both knowledge and humility, a sense of what is known, and a stronger sense of how much remains beyond the beam. Not ignorance as emptiness, but ignorance as an active frontier. The unknown at the bottom of the Pacific is not a blank. It is populated by things we have not yet met. Perhaps in some unvisited trench, chemosynthetic communities line fissures deeper than expected. Perhaps on a seamount not yet filmed, corals grow in forms unknown. Perhaps in abyssal sediment, microbes perform metabolisms not yet described. Perhaps in the water just above the bottom, transparent animals drift past every survey. Perhaps a species with a tiny range lives on nodules in a mining contract area and nowhere else. These possibilities are not fantasies. They are reasonable expectations in a poorly sampled world. Every time exploration improves, the deep grows more complex.
This has happened repeatedly. Dredges found life where none was expected. Vents revealed chemosynthetic ecosystems. Whale falls revealed specialized successions. Hadal cameras filmed fish and scavengers at depths once barely imagined. Molecular tools revealed microbial diversity. Recent trench discoveries revealed deep chemosynthetic communities. The pattern is clear. The deep sea keeps exceeding simplified assumptions. The safest assumption is not emptiness. It is complexity. On the seafloor, complexity can be quiet. A mound of sediment may be the work of an animal. A pit may be feeding behavior. A patch of different color may be microbial process. A faint shimmer may be fluid flow. A cluster of shells may mark a seep. A line of stones may interrupt current. A track may show a passing holothurian. The bottom is full of small inscriptions. Reading them requires slowness. The script itself should imitate that reading. It should not rush from fact to fact as if checking boxes. It should let a footprint become a question become a descent become a landscape become a community become a planetary connection. The style of the reference script moves with accumulation, concept after concept, image after image, expanding from a mystery into systems. For this ocean story, the accumulation should feel less cosmic and more physical. The viewer should feel cold water, pressure, mud, blackness, machine light, living bodies. The philosophy should rise from the place, not arrive from outside. A sea cucumber does not need a thesis. It needs sediment. The thesis, if one emerges, should come from watching it feed. The deep Pacific also invites a different relationship to fear. Fear of depth is ancient and understandable. The ocean can drown, crush, hide, isolate. The deepest places intensify these fears. But fear alone is too narrow. The bottom is not a horror because it is dark. It is not a monster's lair. It is a habitat. Fear can open attention, but if it remains fear, it distorts. The more one learns, the more fear becomes awe, and awe becomes responsibility. A submersible descending through black water can feel terrifying, but when it reaches bottom and sees a small animal moving in the mud, the terror changes. The abyss is still immense, but it is inhabited by ordinary lives. The animal is not there to frighten us. It is there because its ancestors solved a problem. Fear becomes respect. Respect lasts longer. There is also comfort, unexpectedly, in the continuity of deep processes. Marine snow keeps falling. Microbes keep working. Currents keep moving. Animals feed and reproduce. The planet continues its slow exchanges. In a noisy human age, the deep offers not escape, but scale.
It reminds us that Earth is not only the crisis visible at the surface, it is also the patient darkness below, carrying on. This comfort should not become complacency. The deep is affected by human action, but scale can steady the mind. It can make responsibility feel less like panic and more like duty. Panic burns quickly. Duty can endure. At the bottom of the Pacific, endurance is everywhere. A coral enduring current, a sponge enduring cold, a microbe enduring pressure, a nodule enduring time, a trench enduring tectonic stress until it does not, a community enduring scarcity. The word endurance can sound heroic, but here it is simply ecological. Life continues by fitting itself to what is. Humans, faced with the deep, must do a different kind of fitting. We cannot adapt our bodies to the trench quickly, but we can adapt our behavior to knowledge. We can change how we value unseen systems. We can slow decisions. We can improve governance. We can reduce pollution. We can support exploration that is careful rather than extractive. We can let the existence of deep life alter surface choices. This is a moral adaptation. Whether we make it remains uncertain. The Pacific bottom has no guarantee of protection, but it has begun to enter public imagination more vividly. High-definition footage, live-streamed dives, open data, deep-sea documentaries, new discoveries, debates over mining, all bring the abyss closer. The danger is that attention may become entertainment only, a parade of strange creatures detached from place. The opportunity is that attention may become care.
A good image can be consumed quickly. A good story lingers. The aim is not to make the viewer say, "That was strange," and move on. The aim is to leave a trace, like a footprint in mud. Slowly filling, perhaps, but not gone immediately. In a vent field, a plume rises. The camera follows it upward until the chimney disappears below. The plume widens, particles dispersing into black water. Somewhere above, it becomes too dilute to see. Chemicals continue traveling. Microbes may follow gradients. The vent's influence fades into the larger ocean. This is a useful image for the whole deep sea. Local processes spreading outward. Small sources with wider consequences. Hidden systems influencing global ones. A life at the bottom is never only at the bottom. A trench amphipod feeding on a carcass participates in carbon cycling. A microbe oxidizing methane influences greenhouse gas pathways. A sponge filtering water affects particle flow. A coral skeleton records ocean history. A nodule field hosts biodiversity and stores geological time. A vent community changes the definition of habitability. The bottom is not remote from meaning. It is remote from easy access. There is a difference. As the vehicle moves across the Pacific floor, it may pass from soft sediment to basalt. The change is sudden in the light. Mud gives way to dark rock, fractured, pillow-shaped, sometimes coated with sediment, sometimes bare. Basalt is the ocean crust's common stone, born from molten material at ridges and volcanic settings. It is dark because it came from the planet's interior. On land, basalt may form cliffs and columns. Under the Pacific, it forms the foundation of enormous hidden terrains. Life attaches where it can. A sponge here, a coral there, microbial films on rock, small animals in cracks. The rock offers relief in a world of sediment. It also tells a geological story. Cooling lava, spreading crust, volcanic eruption, tectonic transport. In some places, lava flows are fresh enough that sediment has not yet softened them. In others, time has buried and coated the rock. A new flow can erase a community and provide blank substrate for colonization.
The deep sea contains beginnings that look like destruction first. After an eruption at a mid-ocean ridge, scientists may return to find animals gone, chimneys altered, microbial communities changing. Then, over time, colonizers arrive. The sequence reveals resilience and dispersal. It also reveals dependence on regional connectivity. If larvae cannot reach the new habitat, recovery differs. The deep ocean is connected, but not uniformly. A vent field is like an island chain in darkness. Islands can be reached or missed. The metaphor of islands appears often in deep-sea ecology. Vents as islands, seeps as islands, whale falls as islands, seamounts as islands. Each patch of habitat stands out from surrounding conditions, but the metaphor should be used carefully. Unlike land islands surrounded by air and water, deep-sea habitat patches are embedded in a continuous ocean with currents, gradients, and three-dimensional movement. The separations are ecological, not always physical barriers. Still, for a larva needing sulfide-rich flow, the abyssal plain between vents may be as unusable as open ocean is to a land snail. Habitat is defined by the organism. A nodule field may look continuous to us, but for an animal requiring a certain nodule size, sediment type, and food flux, suitable habitat may be patchy. A trench may look continuous on a map, but oxygen, slope, sediment, and food vary. A seamount may be one mountain to us, many zones to its inhabitants. The deep sea teaches perspectival geography. Maps must be made at the scale of lives, not only at the scale of human eyes. This is difficult, but essential. When scientists model species distributions in the deep, they use environmental variables: depth, temperature, oxygen, particulate organic carbon flux, substrate, slope, distance to vents or seeps, current patterns. These models are imperfect, but they help estimate where species or communities might occur. They are especially important because direct sampling is sparse. The Pacific bottom becomes, in data, a probability field. Where life might be dense, where certain habitats might occur, where impacts might spread, where protection might be most effective. The romance of exploration meets the mathematics of uncertainty. Both are part of the modern abyss. A long-form film can show the romance, but it should hint at the mathematics too, not through equations, but through the idea that every image is part of a larger pattern being inferred. A single dive is a line through darkness. Many lines become a map. Measurements become models. Models guide future dives. Future dives correct models. Knowledge loops slowly. The deep sea is not only discovered, it is iteratively approached. Again and again, the bottom revises the map. One of the most beautiful and unsettling things about deep-sea life is its lack of urgency in footage. Many animals move slowly, or appear to. The pace can feel calming, but calm footage may hide intense constraints. An animal moving slowly may be conserving energy because food is limited. A sessile animal may be vulnerable because it cannot flee. A long-lived organism may be slow to recover because it grows slowly. The calm is real, but not simple. A slow world can be a harsh world. The abyss's calm can also lull human viewers into thinking nothing important is happening. We are conditioned to notice speed. A shark strike, a whale breach, a school of fish flashing. The deep often offers a different drama. A mouth opening, a tentacle withdrawing, a particle settling. It requires a lower threshold for attention. This lower threshold may be good for us. It trains perception away from spectacle and toward presence. Not everything alive performs for the camera. At the bottom, most life refuses performance. It simply continues. The voiceover should honor that continuation. not force every moment into climax. The user asked for a script that breathes. The deep sea itself breathes slowly, chemically, physically, through currents and falls and microbial transformations. The narration can follow that breath. Imagine the camera resting on the seafloor for an hour without moving. At first, the scene looks still. Mud, a few stones, suspended particles. Then a small animal crosses the frame. A worm's feeding structure appears and disappears. A faint current shifts the direction of falling snow. A brittle star arm curls. A shadow passes too far away to identify. Sediment settles from the lander's arrival. The longer we watch, the less stillness remains. Stillness was only the first layer. The deep sea often requires duration to reveal itself. Short clips favor the strange and dramatic. Long observation reveals ordinary life. Both matter, but ordinary life is the ecosystem. A vent eruption is exciting, but daily feeding sustains populations. A whale fall is spectacular, but sediment processing is continuous. A new species is thrilling, but the community includes countless familiar functions performed in unfamiliar forms. To understand life at the bottom, one must love the ordinary. This is hard in media, where retention rewards surprise, but long-form storytelling can create another kind of retention. Not shock, but immersion. The viewer stays because the world deepens, because each quiet fact opens another, because the atmosphere becomes habitable for attention. The Pacific bottom is suited to this. It cannot be understood in a minute. It needs descent, wandering, return. It needs the slow turn from nothing is there to how did we ever think nothing was there? The old assumption of deep-sea barrenness was not foolish in a simple way. It came from limited evidence and human intuition. Without sunlight, with cold and pressure, life seemed unlikely to be abundant. Early sampling was difficult, but as tools improved, the assumption failed. This is a useful reminder that science is not a list of eternal statements. It is a method of becoming less wrong when reality answers. The deep ocean has answered repeatedly, sometimes with a worm, sometimes with a microbe, sometimes with a community at a depth no one expected, sometimes with trash. The answer is not always comforting, but it is always information. A plastic bag at full ocean depth is a terrible kind of data. It tells us that human material can reach the deepest seafloor. It turns remoteness into evidence of connection. It is visually simple, morally complex. An object designed for brief use resting in a habitat shaped by million-year processes. The contrast is almost unbearable. A nodule grows for millions of years. A bag is used for minutes. Both arrive on the same floor. This is one of the central images of the modern Pacific bottom, ancient slowness meeting disposable speed. The story should not linger on guilt alone, but it should not look away. The deep sea is beautiful, but beauty does not protect it automatically. Knowledge does not protect it automatically. Even awe does not protect it automatically. Protection requires choices. Still, awe may begin choices. A person who has felt the abyss as alive may be less willing to call it empty. That matters. In the deepest trenches, the pressure is so intense that even chemistry behaves under constraint. Gas-filled spaces collapse, materials compress. Instruments must be calibrated carefully. Batteries, lights, housings, syntactic foam, glass spheres, cables, all must be built for extremes. Failure can be quiet and total. The animals do not carry housings. Their adaptation is internal. Cell membranes remain functional, proteins fold and work, enzymes operate, genetic systems continue, reproduction occurs, development proceeds. Evolution has engineered without blueprints through variation and selection across time. Human machines are impressive because we can design them intentionally. Deep animals are impressive because they are the result of life-solving pressure without intention. Both forms of engineering meet at the bottom. A submersible's titanium sphere beside a snailfish is a meeting between conscious design and evolutionary design. The sphere is there for hours. The fish's lineage is there across generations. The sphere is strong against pressure by resisting it. The fish survives by being compatible with it. Resistance and compatibility. Humans often choose resistance. Deep life often teaches compatibility. This does not mean surrender. It means fitting structure to conditions rather than pretending conditions do not matter. Perhaps there is a lesson there, but it should remain quiet.
The bottom is not a motivational speaker. It is a place.
The Pacific's vastness means there are many bottoms, not one. The eastern Pacific abyss beneath the Clarion-Clipperton Zone differs from the western Pacific trenches. The East Pacific rise differs from the Mariana Forearc. The Kermadec and Tonga trenches differ from the Japan Trench. Continental margins differ from open ocean plains. Even within a single trench, depths and communities vary. The title, Life at the Bottom of the Pacific Ocean, must therefore hold multiplicity. This can be handled not by listing every region, but by moving through representative worlds. The abyssal plain, the nodule field, the seamount, the vent, the seep, the trench, the whale fall, the microbial sediment, the human exploration site. Together they create a portrait, not an encyclopedia. The tone should remain cinematic because the deep itself is spatial and sensory. But the narration must avoid pretending the viewer is watching one continuous dive from all places at once. It can use the idea of a journey, but as a guided drift through the Pacific's lower realms, not a literal, impossible route. The story can move naturally, like a camera dreaming across the seafloor. One moment, abyssal mud, another, volcanic rock, another, a trench slope, another, a cold seep. The continuity is not geography alone. It is theme, life after light. This phrase, life after light, is useful but should not be repeated too often. Its meaning can be carried by images instead. The falling snow, the chemical plume, the soft fish, the tube worm, the patient sponge, the trench amphipod, the footprint. A strong, long-form script trusts the audience to feel connections without being told constantly. The reference script uses accumulation. This script should use immersion. The difference matters. A lecture says, "Now we will discuss." A cinematic voiceover says, "The camera moves." But too much camera language becomes repetitive. Sometimes the narration should simply inhabit the place. The mud is pale. A current crosses the plain. Nothing larger than a hand moves for several minutes. Simple sentences can carry more atmosphere than ornate ones. Variety is part of naturalness. A paragraph of science can be followed by a minimal observation. A poetic image can be followed by a grounded fact. A philosophical thought can be allowed to fade without being crowned. The deep sea's rhythm is not constant grandeur. It includes boredom, quiet, surprise, data, waiting, small humor, unease, tenderness, scale. A sea pig is funny. A plastic bag is not. A vent is astonishing. A nodule is quiet. A trench is oppressive. A microbe is invisible. The script should allow all of that. The viewer should not feel trapped in one emotional register. Hypnotic does not mean monotone. It means the transitions are smooth enough that attention deepens. The emotional rhythm should move like a descent, pressure increasing, light fading, details emerging, then widening into systems, then returning to quiet. At the end, no forced conclusion. The bottom should remain open. The script already returns to the footprint. That is good. Before that, the middle must earn the return by making the footprint part of a whole world. By the time we see it again, it is not just a mark. It is evidence of movement in a landscape of food rain, pressure, geology, microbes, time, and connection. A footprint in deep mud is the smallest possible proof that the abyss is inhabited. It is also temporary. The falling snow will soften it. Sediment will fill it. A worm may cross it. A current may blur it. But for a while, it exists. Many human observations of the deep are like that. Temporary marks against vast darkness. A dive track, a sample, a video frame, a species name, a map line. They may be small, but they change what can be known. The bottom remains mostly dark, but not untouched by understanding. Understanding, if gentle, can be a form of respect. In the Pacific, the deepest places are not evenly distributed. They cluster where plates converge, especially in the western and northern margins, where the Pacific Plate and neighboring plates interact. The ocean's center may hold broad abyssal plains, while its edges contain trenches and arcs. The geometry reflects plate tectonics, and the life reflects geometry. Hadal habitats are long, narrow, discontinuous. Abyssal plains are broad. Vents line ridges and back arc basins. Seeps appear along margins and subduction zones. Geography shapes destiny, even in darkness. A species adapted to a trench may be isolated by shallower barriers, despite living in water. Another species at vents may disperse along ridge systems. A seamount community may be linked to currents crossing open ocean. The Pacific's enormous scale can separate populations long enough for evolution to produce difference. Speciation in the deep sea is not always obvious visually. Two animals may look similar and be genetically distinct. Others may look different but be related. Molecular tools have transformed understanding, revealing cryptic diversity and unexpected connections. The deep sea's true biodiversity may be hidden not only by darkness, but by resemblance. A worm is not always the worm it appears to be. A clam bed may contain multiple histories. A microbial mat may host thousands of lineages. The more precise the tools become, the more the bottom multiplies. This multiplication is exciting and daunting. Conservation becomes harder when what looked like one widespread species becomes many localized ones. Impact assessments become harder when undiscovered diversity is high. But knowledge must complicate policy. Otherwise, policy protects only simplified worlds. The real ocean is complicated. Protection must be worthy of the real ocean. At a deep Pacific vent, some animals may exist nowhere else on Earth. A mining or drilling disturbance, a volcanic event, or natural vent cessation could affect local populations. If similar habitats exist nearby, recolonization may occur. If not, loss could be more serious. Connectivity is a lifeline, but connectivity cannot be assumed. The same applies to seeps and nodule fields. Some organisms may be widespread, others may be local. Some may disperse easily, others may not. Some may recover in decades, others may require centuries or more. The deep sea is not uniformly resilient or uniformly fragile. It is specific. This word, specific, should hover over the whole script like a quiet warning. Do not generalize too quickly. Do not call all darkness empty. Do not call all life abundant. Do not call all disturbance natural. Do not call all slowness weakness. Do not call all remoteness protection. Specificity is respect. A deep-sea octopus brooding eggs on the seafloor offers another kind of deep time. In some deep environments, octopuses have been observed tending eggs for remarkably long periods, far longer than shallow relatives. Cold slows development. A mother may guard the eggs without feeding, slowly giving her body to the next generation. The scene is intimate and severe. An animal in darkness, holding position over eggs for months or years. Even if not every such example comes from the Pacific bottom, it belongs to the larger deep-sea truth. Reproduction at depth can be slow, costly, and vulnerable. A disturbance that removes adults may affect populations for long periods. Life histories matter. An egg in the deep is a promise made slowly. Larvae, when they hatch, may enter the dark water and drift. Some must find rare habitats. The probability seems small, yet lineages persist. Chemical cues, currents, behavior, and sheer numbers may all play roles. The ocean's apparent emptiness hides dispersal pathways built by water movement and evolutionary timing. A larva leaving a vent does not know where the next vent is, but its body carries the inheritance of those that found one. This is both fragile and astonishing. At the scale of one larva, the Pacific is impossible. At the scale of a lineage, it has been crossed. The deep ocean is full of such scale reversals. A tiny organism inhabits an enormous system. A local action accumulates globally. A small chemical gradient supports a large animal. A slow growth process creates a habitat. A brief human decision affects centuries. The bottom repeatedly forces the mind to shift scale, and the narration can use that shifting as momentum. From microbe to trench, from particle to planet, from footprint to ocean basin, from machine light to ancient darkness. This is the structure beneath the story, not chapter headings, but widening circles. The ending should contract again, back to the footprint, because, after all, the vastness, the viewer needs something small enough to hold. The footprint becomes the emotional anchor. It is not dramatic, but it is unforgettable if framed properly. Before the ending, perhaps the script should linger once more in the water above the bottom, because the final rise of the machine will leave the sea floor behind. The transition upward should not feel like escape. It should feel like the light withdrawing from a world that continues. A vehicle leaves a vent field. The chimneys shrink below. The black water fills the frame. Particles drift past. The altimeter increases. The bottom disappears. But the vent continues. Fluid rising, microbes growing, animals feeding, heat moving from rock into ocean. A vehicle leaves an abyssal plain. The mud fades. Tracks and burrows vanish into dark. The sea cucumber continues feeding. A vehicle leaves a trench. The hadal floor disappears beneath thousands of meters of water. Amphipods continue searching. The machine's departure is not the end of the ecosystem. This is important for the final mood. The story should not end as if human observation completes the deep. It should end with life continuing beyond observation. The viewer should feel suspended, not concluded. The final line should not hammer meaning. It should allow darkness to return. Before that final return, one more thought. The bottom of the Pacific is not only the farthest place downward, it is one of the places where Earth most clearly shows that life is not a surface decoration. Life has entered the planet's depths, sediments, cracks, chemical flows, pressure zones. It has followed energy wherever energy appears. It has made homes from mud, bone, stone, metal nodules, sulfur, methane, and falling dust. Life is not everywhere equally, but it is more persistent than human intuition once allowed. This persistence is not loud. At the bottom, it is often pale, soft, slow, microbial, hidden, easily missed. Perhaps that is why it matters so much. A loud world teaches us what can dominate. A quiet world teaches us what can endure. The Pacific bottom is quiet, and it endures. There is no morning at the bottom, but there are beginnings. A current shifts slightly along the sediment, not enough to stir a storm, only enough to change the direction of falling particles. A brittle star adjusts its arms. A small crustacean moves from one depression to another. In the dark, a fish lifts from the mud and glides a short distance before settling again. Nothing in the scene would announce a new day, because days do not arrive here as light. They arrive as changes in flow, scent, chemistry, hunger, and chance. A surface animal measures time by brightness. A deep-sea animal may measure it by food. Somewhere above, dawn spreads over the Pacific. It touches islands, reefs, fishing boats, research ships, floating plastic, the backs of whales, the wings of birds. It warms the upper skin of water and begins another cycle of photosynthesis in the microscopic world. But thousands of meters below, the abyss does not brighten. The news of dawn will travel downward only as matter, and much later. A bloom may form. Tiny grazers may feed, waste pellets may sink, dead cells may fall. The day becomes food after it has stopped being day. This delay is one of the deep ocean's hidden beauties. The bottom receives time after translation. Not sunrise, but carbon. Not weather, but sediment. Not a season, but a pulse in the rain of particles. If spring comes to the surface, the abyss may feel it as a distant increase in food months later. If climate shifts the surface bloom, the bottom may eventually feel that too. The deep sea is not outside the calendar. It reads a calendar written in falling matter. In regions beneath productive waters, the seasonal signal may be stronger. In blue deserts of the open Pacific, the rain may be thinner, more constant, more impoverished. In trenches, material may be focused and gathered. On slopes, currents may sweep food along contours. On seamounts, water movement may intensify feeding opportunities. A deep animal's life depends not only on depth, but on what the surface above has been doing, sometimes far away. The surface is a distant weather system for the bottom, and geology is another. At a vent field, the day begins when the flow changes. A crack widens, a chimney breaks, a new opening releases warm fluid, a plume shifts, bacteria grow in a slightly different patch, shrimp move closer, then away. At a seep, methane flow may strengthen or weaken. At a trench, an earthquake may send a cloud of sediment downslope. On an abyssal plain, a carcass may land and transform the neighborhood. The deep sea's events are not synchronized by sunlight. They are synchronized by energy. Energy is the hidden clock. Where energy is steady, life can settle into patience. Where it is sudden, life must be ready. Where it is chemical, life must partner with microbes. Where it is rare, bodies become economical. Where it is concentrated, communities crowd. Where it disappears, animals leave or die. This is the simplest way to understand the bottom of the Pacific. Follow the energy, and the life begins to make sense. Marine snow is one path. Hydrothermal chemistry is another. Methane seepage is another. Whale bones are another. Wood falls, kelp falls, fish carcasses, sedimented carbon, microbial reactions inside mud, each is a path by which energy reaches the dark. The animals are arranged along these paths like travelers along roads. Some roads are broad and faint, like the constant fall of particles over the abyssal plain. Some are narrow and intense, like a vent crack. Some are temporary, like a whale fall. Some are hidden beneath the mud, like microbial methane production. Some are ancient, like the slow accumulation of organic carbon in trench sediments. The bottom is a map of energy roads, most of them invisible. A camera sees the travelers. Science tries to infer the roads. A field of clams reveals a seep road. A swarm of amphipods reveals a carcass road. A bacterial mat reveals a chemical road. A sponge field reveals a current road. A barren-looking plain may still hold a faint road through the mud, traveled by microbes and deposit feeders too small to dramatize.
To live at the bottom is to find a road where almost no road seems to exist. The Pacific's enormity makes this especially moving. Across distances so large they seem to defeat connection, animals still find each other. Larvae find habitat. Microbes find gradients. Scavengers find food falls. The success is never guaranteed. Countless larvae must fail. Countless particles are consumed before reaching the floor. Countless carcasses may land where few specialists find them. The system is not efficient in a human industrial sense. It is abundant in attempts. Evolution works with attempts. The bottom we see is the result of attempts that continued long enough to become lineages. A tubeworm lineage learned to live with bacteria. A snailfish lineage learned pressure. A sponge lineage learned filtration in cold darkness. A worm lineage learned bone. A clam lineage learned seepage. Microbes learned almost everything first. Microbes are the oldest patients in the story. They were here before animals, before fish, before whales, before forests that could fall into the sea, before humans could wonder about any of it. At the bottom of the Pacific, microbes remain central not as relics, but as active makers of habitability. They process carbon, oxidize methane, reduce sulfate, build mats, inhabit symbioses, colonize vents, alter minerals, and continue in sediments where energy is scarce enough to make life seem almost paused. Almost paused is not stopped. A microbe living slowly in deep sediment may not fit human excitement, but it stretches the definition of activity. Its life may be measured in chemical maintenance, rare division, survival under limitation. It suggests that life does not always need to be busy to be alive. This idea is difficult in a culture that equates vitality with speed. The abyss offers a slower definition. Vitality can be persistence. It can be maintenance. It can be a cell keeping its chemistry intact in dark mud. It can be a sponge filtering invisibly for decades. It can be an octopus guarding eggs in cold water. It can be a community waiting for the next fall. If the surface ocean is a place of motion, glitter, chase, and bloom, the bottom is often a place of continuation. Not always. Vents can be furious. Carcasses can be frantic. Landslides can be violent. But the baseline is continuation. The bottom's drama is stretched thin across time.
A human life may be too short to see certain changes clearly. That does not make them small. A nodule growing across millions of years is not small. A sediment layer accumulating across glacial cycles is not small. A coral recording centuries of water chemistry is not small. A trench forming through plate motion is not small. It is only slow. The Pacific bottom is a monument to the fact that slow things can be enormous. This may be one of the hardest lessons for humans to absorb. We notice the sudden and underestimate the slow. But climate, evolution, sedimentation, deep circulation, tectonics, and ecological recovery all move through slow power. Disturb the slow world quickly, and the consequences may be difficult to reverse, not because the damage is visually dramatic, but because the processes of repair are slow. A track in abyssal mud can outlast careers. A removed nodule will not regrow on human timescales. A broken coral may not be replaced for centuries. A species lost before description leaves not only an ecological absence, but a permanent ignorance. The bottom's quiet makes consequences easier to ignore and harder to forgive. On a research vessel, after a dive, the footage is reviewed. Hours of mud may pass on screen. Notes are taken, species are marked, behaviors are logged. A casual viewer might skip ahead, looking for the spectacular animal. The scientist watches the mud. There may be tracks. There may be density changes. There may be evidence of feeding, burrowing, current direction, disturbance, substrate use. The mud is data. Learning to watch mud is a deep-sea skill. It is also a moral skill. It means granting significance before glamour appears. The same skill applies to the human future of the Pacific bottom. We must decide that a place matters before it becomes a catastrophe, before images of loss become dramatic, before rarity becomes extinction. The deep ocean's slow injury may not provide the kind of spectacle that triggers public action. Protection must come from foresight. Foresight is attention extended into the future. The abyss is attention extended into the past. Between them, human choice stands briefly. There are places in the Pacific where the bottom is shaped by ashes from eruptions, by dust from Asia, by the shells of organisms that lived in surface waters thousands of kilometers away, by landslides from continental margins, by the fall of animals that migrated across ocean basins. The sediment is a mixture of far origins. A handful of mud is a geography lesson. It contains continents, volcanoes, plankton, climate, currents, and time. A worm feeding in it does not separate these origins. It takes the mud as it is. But humans can separate them analytically and then put them back together imaginatively. The result is a more complete sense of place. Not empty gray ooze, but compressed planet. The bottom of the Pacific is where Earth gathers itself. This gathering is not always gentle. Trenches gather material through violent tectonics. Sediment slides gather and bury. Carcasses gather scavengers. Pollutants gather through food webs. Metals gather atom by atom into nodules. The bottom is a zone of concentration as much as dispersal. What falls apart above may come together below. A dead whale becomes a community. A dissolved metal becomes a nodule. A chemical seep becomes a clam bed. A rain of plankton becomes sediment. A human object becomes evidence. The abyss is a collector. This makes it powerful and vulnerable. Collectors accumulate richness, but also contamination. The same processes that deliver food can deliver toxins. The same sinking that moves carbon can move plastic. The same food webs that nourish animals can concentrate pollutants. The deep sea is downstream not only of nature, but of civilization. Downstream is another word that changes the story. We often think of the deep as far away, but downstream is not far away morally. It is connected by flow. The bottom receives what systems send to it. The Pacific bottom receives from rivers, atmosphere, ships, fisheries, industry, climate, and surface life. It is hidden downstream. A hidden downstream is easy to abuse. A known downstream is harder. Story can turn hidden into known. Not fully known, never fully, but known enough to matter. In the final years of the 19th century, the idea that life existed in the deep sea had already gained evidence, but the richness and complexity of deep ecosystems were still beyond imagination. In the 20th century, submersibles and oceanographic expeditions expanded the picture. In the late 1970s, hydrothermal vents transformed it. In the decades since, each new technology has opened another layer. ROVs, AUVs, landers, molecular sequencing, pressure labs, high-definition cameras, satellite-guided mapping, environmental DNA. The bottom has not changed because humans improved tools. The human picture has changed. This distinction matters. Discovery is not creation. The vent worms were not born in 1977. The Hadal microbes did not appear when sampled. The trench communities did not begin when published. They entered human knowledge then. They had their own histories before that. The deep ocean is full of pre-existing revelations. Every discovery is late. There is humility in arriving late. It means the first duty is not to proclaim, but to listen. Listening in the ocean can be literal. Hydrophones record sounds humans cannot hear from the surface. Earthquakes, whales, rain, ships, ice, perhaps geological activity. At depth, sound travels through the water column, bending and channeling. The deep soundscape includes events from far away. A whale's call may cross distances that would feel impossible in air. A ship's engine may intrude into places where no ship is visible. The bottom, though dark, is acoustically connected. This connection has implications for noise pollution. As human activity expands, even remote marine environments can become louder. The effects on deep-sea species are not fully known, but uncertainty is not absence of effect. Animals that sense vibration, use sound, or respond to pressure waves may be influenced. Again, the deep asks us to consider impacts we cannot easily see. The visual imagination must be joined by an acoustic imagination. Imagine the bottom not as silent black, but as a dark room where distant storms murmur, earthquakes crack, whale calls pass like low weather, and human engines thread through water from above. An amphipod may not hear as we do, but the water is moving with signals. A fish may sense vibration. A squid may respond to pressure changes. The abyss is not mute. Even silence, if present, would be a condition worth protecting. There are few silences left on Earth untouched by human machinery. The deep sea may hold some of the last large acoustic spaces, though even they are increasingly crossed by sound. A camera cannot show this directly. A script can. Sound gives another way to make the bottom present. The creak of a submersible hull, the soft hiss of electronics in a control room, the imagined low thunder of an earthquake through water, the absence of waves at the sea floor, the fact that storms above become pressure and motion below only indirectly, the quiet feeding of animals without voices humans can hear. The bottom is sensory, but not in human proportions. Touch may matter more. Chemical sense may matter more. Pressure may matter more. Light may be rare and self-made. Sound may travel differently. The deep sea's sensory world is not impoverished, it is reorganized. A long-form voiceover can invite the audience into that reorganization. It can ask them to let go of sunlight as the primary way of knowing. It can make chemistry feel like landscape, pressure like weather, sediment like archive, darkness like habitat.
The best ocean stories do not simply show new creatures, they teach new perception. By the time the story nears its end, the viewer should not look at black water the same way. Black water should feel inhabited. Mud should feel active. Depth should feel connected. The Pacific surface should feel like the lid of a world rather than the whole world. This changed perception may be quiet, but it is powerful. It means the next time someone says, "the bottom of the ocean," the mind does not picture nothing. It pictures a pale animal crossing mud, a vent chimney breathing minerals, a tube worm's red plume, a trench amphipod at bait, a sponge on a nodule, a whale skeleton becoming habitat, microbes working in sediment, a submersible light shrinking as it rises. It pictures life. Not life as abundance everywhere, life as persistence everywhere it has found a way. There is a difference, and the difference is the truth. Before the final ascent, there is one more landscape to cross. The place where the ocean floor looks almost like the surface of another moon. The mud is pale, but not smooth everywhere. It is stippled by tiny pits, crossed by faint trails, marked by small mounds and collapsed openings. Some marks were made hours ago. Some may be much older. In the deep sea, time leaves soft evidence. A track does not vanish under rain. A footprint is not erased by wind. It waits for sediment, for current, for another animal, for the slow settling of the world. A camera moves low over this terrain, and the lights make shadows where no natural shadow would exist. The shadows help the human eye. They turn slight relief into visible form. A burrow becomes a black crescent. A mound becomes a hill. A worm tube becomes a tower. The landscape is tiny and immense at once. This is one of the deep ocean's constant tricks. The scale keeps changing. A depression the size of a hand may matter to a small animal like a valley. A nodule the size of a potato may be a foundation. A whalebone may be a ridge. A bacterial mat may be a pasture. A vent chimney may be a mountain. A trench may be a world. To understand the bottom, one must repeatedly become smaller, not physically, but imaginatively. The human scale is not the correct scale for most of what matters there. Human eyes look for cliffs, monsters, forests, obvious movement. The abyss offers grains, films, openings, slow mouths, soft bodies, chemical boundaries. The story becomes richer when the mind lowers itself to those scales. A grain of sediment is not just a grain if a microbe lives on it. A film is not just a film if it feeds a snail. A crack is not just a crack if it brings sulfide into oxygenated water. A stone is not just a stone if a sponge can anchor there and lift itself into the current. The bottom is built from small permissions. Hard substrate permits attachment. A chemical gradient permits chemosynthesis. Falling carbon permits deposit feeding. Oxygenated water permits animal metabolism. A current permits filtration. A carcass permits scavenging. A trench shape permits accumulation. These permissions are not generous in a human emotional sense.
They are conditions. Life finds them, tests them, inherits them. Where permission is absent, life thins. Where it appears, life gathers. At the edge of a bacterial mat, a small snail may graze. Its shell reflects the vehicle's light. Nearby, the mat itself is a living sheet made of countless cells, each too small to see individually. The snail's life depends on something it can consume but not understand. The microbe's life depends on chemistry rising from sediment or rock. The chemistry depends on geology, buried carbon, fluid pathways, pressure, temperature. The chain is long, and no part of it knows the whole. Humans may be the first creature in the chain trying to imagine all of it. That effort is beautiful and dangerous. Beautiful because it widens sympathy. Dangerous because understanding can be mistaken for possession. To describe a system is not to own it. To map a habitat is not to make it available. To name a species is not to reduce it to a label. Knowledge should make the deep more real, not more convenient. The Pacific bottom has spent most of Earth's history outside human convenience. It has no roads, no breathable air, no easy light, no simple rescue, no familiar distances. This inconvenience is part of what preserved it for so long. But technology is changing the meaning of inaccessible. What could not be reached can now be reached. What could not be mapped can now be mapped. What could not be extracted may soon be extractable. The old protection of difficulty is weakening. The new protection must be choice. Choice requires imagination strong enough to include the unseen. It requires science patient enough to measure what does not perform. It requires a culture willing to say that some places should not be treated first as inventory. It requires admitting that mystery is not a gap waiting only to be filled, but sometimes a condition worthy of respect. The deep ocean is not sacred because it is untouched. It is not untouched. It is sacred, if that word is allowed, because it is real beyond us. A small fish turns in the beam, and the light catches its eye. For one instant, the eye shines back. The exchange is accidental. The fish is not recognizing humanity. It may be startled, indifferent, attracted, or simply passing. But the image can still move us, because it feels like contact across impossible difference. Then the fish is gone. The beam finds mud again. This is how the deep gives itself, not as possession, but as encounter. Encounter after encounter, partial and brief, building into a larger sense of presence. At the end of a long dive, the vehicle may carry samples, data, and hours of footage. It may also carry scratches, sediment on its frame, perhaps a minor failure, perhaps a manipulator that moved less smoothly after hours in cold water. It has touched the bottom and returns altered. The people watching return altered too, though more quietly. They have seen a world where the ordinary rules of human life do not apply, and yet life continues. This is the emotional center of the story. Not danger, not spectacle. Continuance. Life continues without light, without warmth, without ease, without audience. It continues in mud, rock, water, bone, chemistry, and pressure. It continues slowly, locally, specifically. It continues even as humans struggle to understand whether to admire it, study it, use it, protect it, or leave parts of it alone. The bottom does not answer that struggle for us. It simply remains alive while we decide. In the Pacific, above every deep place, the surface keeps moving. The ocean does not show its depth to the sky. Clouds pass over trenches without knowing them. Moonlight touches waves above abyssal plains. Flying fish break the surface over landscapes they will never see. Whales dive partway into darkness and return to breathe, never reaching the deepest floor, but linking worlds with their bodies. Ships cross, storms build, satellites measure. Humans name routes and borders on a surface that hides the vertical majority of the planet. Most of the living space on Earth is ocean, and much of that is deep. This fact is repeated often, but its meaning is rarely felt. It means the familiar human world is not the main volume of life's planet. It means Earth is not primarily the landscape we walk through. It means the blue part of maps is not flat. It means the bottom of the Pacific is not marginal. It is part of the vast interior of the living Earth. The abyss is not at the edge of the world. It is under the middle of it. And because it is under, it is easy to forget. A good story should make forgetting harder. It should leave the bottom somewhere in the mind, dark but not blank, distant but not disconnected. It should make the next image of the Pacific surface feel deeper, as if every wave carries the hidden weight of plains, vents, seeps, trenches, animals, microbes, and time. Then the title, Life at the Bottom of the Pacific Ocean, no longer sounds like a curiosity. It sounds like a doorway. Not a doorway we can walk through easily. A doorway we lower ourselves toward, slowly, with lights, instruments, caution, and the uneasy knowledge that someone already lives on the other side. There are moments in deep-sea footage when the vehicle stops moving and the water itself becomes visible. Not as blue, not as a wave, not as the thing people swim through, but as a black volume full of drifting points. Particles cross the light at different speeds. Some rise in the turbulence made by the machine. Some fall with their own slow patience. Some move sideways with a current too gentle to feel from the surface. The water looks almost like space, except every point in it may once have been alive, or may be carrying life too small to see. In that suspended field, the boundary between ocean and sky seems to reverse. At the surface, people look up at stars and feel small. At the bottom, the machine looks into falling particles, and the feeling is similar, but more intimate. These are not distant suns. They are remains, nutrients, cells, fragments, future sediment. They are the sky of the abyss, and they are close enough for an animal to eat. A sea cucumber raises its feeding tentacles into that slow fall. The gesture is simple, almost tender. It is not reaching for beauty, it is feeding. But the image holds both meanings because humans cannot fully separate them. The tentacles gather what the ocean offers. A moment later, they fold inward, delivering the captured particles to the mouth. The animal continues. This is life reduced to its essential transaction with the world. Receive, transform, continue. Every ecosystem does this, but the deep sea shows it without ornament. There are no leaves fluttering, no flowers, no birdsong, no sunlight warming the scene. There is matter falling through darkness, and the body adapted to take it in. The simplicity is not primitive, it is profound because it is enough. Nearby, another animal leaves a trail that curves out of the beam. The mark is fresh, its edges sharp. It may be gone in time, but not soon. The abyss keeps handwriting slowly. Each track is a sentence without words. I passed here. I fed here. I turned here. I was alive here. The sea floor is covered in such sentences. Most will never be read. Some will be crossed by cameras. Some will be buried. Some will be destroyed by a slide or a machine. Some will simply soften into the background of the mud. But for a while, they make the invisible lives of the bottom visible. Perhaps this is why the deep ocean feels so moving when it is finally seen. It is not only that the animals are strange, it is that they have been living in a darkness that did not require our witness, leaving traces for no audience, participating in cycles older than our species. The camera arrives late, shines briefly, and discovers not a beginning, but a continuation already underway. That continuation is the real mystery. Not how life can exist in one spectacular place, but how many forms of life have quietly made the bottom ordinary to themselves. The abyss is extraordinary to us because we cannot live there. To its residents, it is the given world. Cold, dark, pressurized, sparse, chemical, immense. They do not overcome it, they are made of it. A final survey line might pass over a region where nothing large appears for several minutes. The screen shows sediment and snow. Then, a single worm tube rises from the mud. Then another track. Then a small, pale animal half buried, withdrawing as the lights approach. The scene does not explode into revelation. It does something better. It asks the watcher to lower the threshold of wonder. The Pacific bottom is full of lives that will only be noticed by a lowered threshold. And maybe that is the beginning of a different kind of seeing. It also asks that the darkness be allowed to remain more than a backdrop, because for countless lives, it is the whole country. The ending of this story cannot be a conclusion, because the bottom of the Pacific is not concluded. It is still being mapped, sampled, misunderstood, revised. New ecosystems have been found in the Hadal Zone. New species are described. New technologies extend reach. New threats emerge. New questions open under old assumptions. The story is not a line from ignorance to knowledge. It is a widening darkness with more lights in it. Every answer reveals more seafloor beyond the beam. There may be vent fields undiscovered along remote ridges, seeps hidden along trench slopes, species living across nodule fields uncollected, microbes in sub-seafloor habitats with metabolisms unknown, trench communities that complicate what hadal life can be, ancient corals recording centuries of ocean change, fish, worms, jellies, sponges, clams, crabs, amphipods, and organisms without common names carrying on in darkness. To say life at the bottom of the Pacific Ocean is not to describe a single life. It is to describe many ways of surviving after the sun is gone. Some wait for the fall. Some gather at the crack. Some root in chemical mud. Some roam the trench. Some filter the invisible. Some eat the dead. Some live inside others. Some barely seem to move at all. And all of them, together, make the bottom not an ending, but a continuation. The camera returns to the footprint. By now, the animal that made it is gone. The sediment around the mark has softened. A few particles drift down through the light and settle into the hollow. Another hour passes, or a day, or a year. The ocean does not hurry to erase it, but erasure has already begun. Above, the Pacific moves under weather. Waves rise and collapse. Ships cross. Clouds form. Plankton bloom. A whale breathes, dives, rises again. Sunlight scatters over blue water. Somewhere, a storm builds. Somewhere else, the surface is calm enough to mirror the sky. None of that light reaches the footprint, but the surface is there in it anyway. In the dust that falls, in the oxygen dissolved in the water, in the carbon inside the mud, in the eventual meal of an animal that has never seen day. The bottom of the Pacific is not separate from the world. It is the world at its most hidden, most pressured, most patient. It is a place where mountains drown, where valleys deepen past imagination, where chemistry becomes food, where life moves slowly through darkness and leaves small marks behind. A pale amphipod crosses the edge of the beam. A worm withdraws into its tube. A fish hovers just beyond sight. The machine's lights tremble as it rises, lifting away from the mud. The circle of brightness narrows, then leaves. Darkness returns completely. And at the bottom, beneath the great weight of the Pacific, life continues without needing to be seen.